Hello there, and welcome to Physics with William. This is a quiet place for thinking slowly about how the universe works, without rushing, without pressure, and without the feeling that you need to remember every detail. It's a space where ideas are allowed to unfold at their own pace, where curiosity is welcome, and where science is treated less like a test and more like a long conversation you can ease into at the end of the day. Tonight, or this morning, or wherever this moment happens to fall for you, we're going to spend some time with a question that sounds simple on the surface but turns out to be anything but. It's a question that hides in plain sight, wrapped inside things we see every day, and yet rarely stop to think about for more than a few seconds at a time. That question is why motion never really ends. We live in a world that seems full of stopping points. Cars brake at intersections. Fans slow down and fall silent. A tossed ball rises, hesitates, and then comes back down to rest in someone's hand or on the ground. At first glance, motion looks temporary. Things move, and then they stop. That's the story our senses tell us, and it's a convincing one. After all, when you slide a book across a table, it doesn't glide forever. It slows, it wobbles, and eventually it comes to a halt. When you jump, you don't keep drifting upward. Gravity brings you back. When you stir a cup of tea, the swirling patterns fade and the liquid settles into stillness. It feels natural to assume that motion is something that has to be actively maintained, and that without constant effort, the universe prefers things quiet and unmoving. But that intuition turns out to be misleading, not because our senses are broken, but because they're tuned to a very narrow slice of reality. We notice motion when it's large enough to track with our eyes and hands, and we notice stillness when those motions drop below our ability to detect them. What we don't notice is that beneath that apparent calm, something else is always going on. Motion doesn't disappear. It changes form, shifts scale, spreads out, and becomes harder to recognize, but it doesn't vanish. The universe doesn't have a built-in pause button. It has no natural preference for rest. What it has instead is energy, and energy has a stubborn habit of continuing in one form or another. Before we get any deeper into that idea, it might be worth slowing down for a moment and anchoring this conversation in something personal. Where are you listening from right now? Are you sitting still, or are you moving as you listen? Maybe you're lying down, maybe you're walking, maybe this is playing softly in the background while you do something else. And what time is it for you, not just on a clock, but in your day? Early, late, somewhere in between. These details don't change the physics, but they do change how we experience it. Energy and motion don't exist in isolation from us. We're part of the system too, breathing, shifting, thinking, burning fuel just to remain upright and aware. If this kind of slow, steady exploration is something you enjoy, or if you find it helps you unwind while still giving your mind something solid to rest on, then liking the video or subscribing really does help. It keeps this channel going and lets more people stumble into these conversations when they need them. There's no urgency there, just a quiet invitation, much like the rest of what we're doing here. Now, when we talk about motion never ending, it's easy to slip into vague language or philosophical statements that sound impressive but don't explain very much. That's not the goal here. What we're going to do instead is build the idea carefully, starting from familiar experiences and gradually widening the lens. The claim isn't that objects you push will keep sliding across your kitchen floor forever, or that visible movement never slows. The claim is more specific and more interesting. It's that the quantity responsible for motion, the thing that allows movement to exist at all, doesn't get destroyed when motion appears to stop. It gets redistributed, it gets transformed. It sinks into places that are harder to see, harder to track, and harder to reverse. That quantity is energy, and even though we use the word constantly, it's one of the most misunderstood concepts in science. Energy gets talked about as if it were a substance, like a fuel or a fluid, something you can pour into a system or run out of entirely. We say we're low on energy, that a battery has energy, that a moving object has energy, that heat is energy, that light carries energy. All of that is true in different ways, but it can leave the impression that energy is a thing you can point to, separate from motion and change. In reality, energy is better thought of as a bookkeeping tool. It's a way of keeping track of the capacity for change within a system. When something moves, heats up, emits light, or changes its internal structure, energy is how we account for that activity in a consistent way. One of the most important discoveries in physics is that when you do that accounting carefully enough, the numbers always balance. Energy doesn't appear from nowhere, and it doesn't disappear into nothing. It moves between forms, it spreads out. It becomes less useful for doing certain kinds of work, but it never truly goes away. That simple statement has consequences that reach far beyond classroom diagrams or textbook problems. It applies to falling objects and orbiting planets, to chemical reactions and electrical circuits, to living cells and entire ecosystems. It even applies to the expansion of the universe itself. But before any of that starts to feel overwhelming, it helps to return to something small and concrete. Imagine pushing that book across the table again. You give it a shove, and it slides forward. At first, it moves quickly, then more slowly, and finally it stops. From your point of view, the motion is gone. The energy you put into the book seems to have vanished. But if you look more closely, that energy didn't disappear. It was transferred into the table as tiny vibrations. It warmed the surfaces of both the book and the table by an amount too small to feel. It stirred the air molecules around it. The motion you could see turned into motion you can't. On a microscopic level, the system is more active after the book stops than it was before you touched it. This idea runs counter to how we naturally interpret rest. Stillness feels like the absence of activity, but in physics, stillness is usually just a balance of motions cancelling each other out, or dropping below our detection threshold. Even an object sitting quietly on a table is full of internal movement. Its atoms vibrate. Its electrons shift and interact. The surrounding air collides with its surface trillions of times per second. The only reason it appears motionless is that all of this activity averages out into something stable at our scale. The same principle applies when motion seems to fade away over time. A swinging pendulum eventually comes to rest, not because motion has been destroyed, but because its energy has been siphoned off into the air, and the support structure is heat and sound. A spinning wheel slows down, not because motion is being erased, but because friction transfers that organized rotation into random microscopic movement. The universe doesn't eliminate motion, it redistributes it until it's spread thin. This redistribution is so reliable that it's become one of the foundational rules of physics. It doesn't matter whether you're talking about classical mechanics, electromagnetism, thermodynamics, or quantum theory. At every level, energy conservation shows up, sometimes dressed in different mathematical clothing, but always telling the same story. Motion doesn't end, it migrates. What makes this especially interesting is that our everyday experience trains us to expect the opposite. We grow up in an environment where friction is everywhere. Air resistance, surface roughness, internal losses in materials, all of these effects drain visible motion quickly. We almost never encounter systems that are free to keep moving without interference. When we do, they tend to feel unnatural or even magical. An ice puck gliding across a nearly frictionless rink. A satellite orbiting Earth without slowing down. A superconducting current that flows without resistance. These systems don't violate the rules we're used to. They reveal what the rules actually are when the usual sources of energy transfer are minimized. Once you start thinking in these terms, motion stops looking fragile and starts looking persistent. The real question shifts from why things move to why motion ever appears to stop at all. And the answer to that question has less to do with motion itself, and more to do with how energy spreads and how systems interact with their surroundings. There's also a deeper implication hiding here, one that connects motion to time, change, and irreversibility. When energy spreads out, it becomes harder to gather back into a single organized form. That's why a moving object that slows down doesn't spontaneously speed back up in the same direction. Not because it's forbidden, but because the energy required to do so is now scattered across countless microscopic degrees of freedom. Motion hasn't ended, it's just no longer concentrated in a way that produces large-scale movement. This distinction matters because it prevents us from confusing stillness with inactivity and stopping with ending. From the perspective of physics, the universe is never static. Even in its quietest moments, it's in motion, at scales we can't directly sense. The night sky may look calm, but planets are racing along their orbits. Atoms in your body are vibrating. Radiation from distant stars is passing through you right now. The idea of a truly motionless state turns out to be an abstraction, not something the universe actually achieves. As we move forward, we'll take this basic insight and apply it in different contexts, from simple mechanical systems to thermal processes, from atoms to galaxies, from living organisms to the cosmos as a whole. Each step will add detail without breaking the thread. The central idea remains the same. Motion doesn't disappear, it changes form. Energy doesn't get used up, it gets redistributed. And as we continue, the focus will gradually shift from objects you can see and touch to processes that unfold over longer timescales and larger distances, where the persistence of motion becomes even more striking. Because once you stop thinking of motion as something that needs to be constantly fueled, and start thinking of it as something that only changes shape, the universe begins to look very different. Not like a machine that winds down, but like a system that endlessly rearranges itself, never fully coming to rest, even when it seems quiet on the surface. Most of the time, motion doesn't feel mysterious at all. It feels obvious, almost boring. Things move because something makes them move, and then, eventually they stop. That pattern is so familiar that we rarely question it. You push a door and it swings open. You roll a ball and it slows down. You pedal a bicycle, and when you stop pedaling, the bike coasts for a bit and then comes to rest. Nothing about this seems puzzling. It feels like common sense, the kind of understanding you don't need to articulate because it matches what your body has learned through years of experience. And yet, buried inside these ordinary moments is a contradiction so deep that it took centuries for physics to untangle it properly. The contradiction is this: if motion really needed a cause to continue, if the natural state of the universe were rest, then the world would behave very differently from how it actually does. Motion would be fragile. It would constantly need to be propped up by forces pushing and pulling, and the moment those forces disappeared, everything would freeze into stillness. That sounds reasonable when you're standing on Earth, surrounded by friction, air resistance, and surfaces that scrape and grind against one another. But when you strip those effects away, the picture changes completely. Motion turns out not to be something that has to be maintained, but something that only stops because it is interfered with. The reason this feels counterintuitive is that we almost never experience motion in isolation. From the moment we're born, we're immersed in an environment that aggressively dampens movement. Air presses back against anything that moves through it. Surfaces rub against each other. Internal friction inside materials converts organized motion into heat. These effects are so ubiquitous that we mistake them for fundamental rules of nature rather than side effects of our surroundings. We grow up thinking that motion fades because that's what motion always seems to do. We don't notice that what's really happening is a constant transfer of energy into places we're not paying attention to. Take something as simple as walking across a room. You lift your foot, move it forward, and place it down again. The motion feels smooth and deliberate, but every step involves a cascade of interactions. Your muscles contract, converting chemical energy into mechanical motion. Your foot pushes against the floor and the floor pushes back. Tiny deformations ripple through the materials involved. Heat is generated in your muscles, your joints, and the ground beneath you. Sound waves spread outward as your foot makes contact. None of that energy disappears. It's just redistributed across many channels, most of which don't register consciously. Because this redistribution happens quickly and invisibly, our brains simplify the story. We tell ourselves that motion happened and then it stopped. That simplification is useful for everyday life. It helps us predict outcomes well enough to function. But it obscures what's actually going on. Motion doesn't end. It fragments. It diffuses. It becomes less obvious. There's another reason motion feels straightforward, and it has to do with effort. We associate motion with exertion. If something is moving, someone or something must be doing work to keep it going. If it's not moving, we assume no work is being done. This mental shortcut works reasonably well for human-scale activities, but it breaks down the moment you look beyond them. A planet orbiting a star isn't constantly firing engines to stay in motion. An electron moving through a conductor doesn't need encouragement to keep drifting. A beam of light doesn't get tired as it crosses interstellar space. In all of these cases, motion persists not because something is pushing continuously, but because nothing is stopping it. This idea clashes so strongly with everyday intuition that early thinkers struggled with it for a long time. For much of human history, motion was thought to require a continuous cause. If an object was moving, there had to be a force acting on it. If that force stopped, the motion would stop too. This view wasn't unreasonable. It matched what people observed in daily life. Throw a stone, and it eventually falls to the ground. Stop pulling a cart and it slows down. The mistake wasn't in the observations, but in the interpretation. Friction and resistance were quietly doing most of the work, but they weren't recognized as separate effects. Motion was being blamed for its own disappearance. Even now, knowing the physics, it's hard to shake that instinct. When you see a car cruising down the highway, it feels like the engine is what keeps it moving. In reality, the engine's job is mostly to counteract losses. If there were no air resistance and no friction in the tyres or drivetrain, the car wouldn't need to keep burning fuel to maintain its speed. It could coast indefinitely. The engine isn't sustaining motion. It's fighting everything that's trying to drain energy away from that motion. The everyday mystery, then, isn't why things move. It's why motion seems so temporary when the underlying rules say it should be persistent. The answer lies in the sheer number of ways energy can leak out of a visible form. Every surface you touch, every fluid you move through, every material you bend or compress provides pathways for energy to spread out. Once it does, it's no longer concentrated enough to produce the kind of motion you can easily see. This is why a sliding book stops, but a planet keeps going. The book is embedded in an environment designed to sap motion. The planet is not. Space is remarkably empty. There's very little to rub against, very little to collide with. Once a planet is set moving, it stays that way, following its path not because something keeps pushing it, but because there's nothing substantial to slow it down. From the planet's perspective, continuing to move is the simplest option. What's interesting is how quickly our intuitions flip when we change context. If you watch footage of astronauts inside a space station, objects don't behave the way you expect. A gentle push sends them drifting across the cabin. They don't slow down unless they bump into something. The first time you see it, it looks strange, almost comedic. But that strangeness is just your everyday assumptions being exposed. You're seeing motion without its usual restraints. Even on Earth, there are hints of this behaviour if you know where to look. An air hockey puck glides far longer than a normal puck because the cushion of air reduces friction. A curling stone slides across ice much farther than seems reasonable because the ice surface is engineered to minimise resistance. These systems feel special, but they're actually closer to the fundamental behaviour of motion than most of what we experience day to day. Another layer of the mystery comes from how we perceive beginnings and endings. Motion often appears to start suddenly and end definitively. A light turns on, a machine powers down, a person stops walking. These events feel discrete, but when you look closely, the transitions are gradual and continuous. The light doesn't appear instantly. Electrical currents build up, electrons drift, fields rearrange. When the machine stops, Internal components are still vibrating, still warm, still exchanging energy with their surroundings. When a person stops walking, their heart keeps beating, their lungs keep moving, their body continues a complex internal dance of motion that doesn't pause just because their feet are still. We draw boundaries around motion because it helps us categorize the world, not because those boundaries are physically sharp. From the universe's point of view, there is no clear line between moving and not moving. There are only different patterns of activity, some more obvious than others. This becomes even clearer when you consider motion at scales we don't usually think about. At the microscopic level, everything is in constant motion. Atoms vibrate, molecules collide, particles jitter due to thermal energy. Even in a solid object that feels rigid and unmoving, the internal components are anything but still. The rigidity itself is a result of dynamic balance, not static rest. Forces pull and push at incredibly small distances, locking structures into place through continuous interaction. Temperature is one way this hidden motion makes itself known. Heat is not a substance, it's a measure of microscopic motion. When something heats up, its internal particles move more vigorously. When it cools down, they slow, but they never completely stop. Absolute zero, the theoretical point where all motion ceases, turns out to be unreachable. The closer you get, the harder it becomes to remove the remaining energy. Motion persists stubbornly, even in the coldest conditions we can create. This persistence is not a coincidence. It's built into the way energy behaves. Energy doesn't like being confined to a single, simple form. Given the chance, it spreads out. It explores the available options. It finds new ways to move. What looks like an end to motion is usually just the beginning of a more complicated distribution. The everyday mystery of motion is also tied to how we think about cause and effect. We're used to linking motion to forces directly. Push equals movement. No push equals no movement. But in physics, forces are better understood as agents of change, not sustainers of state. A force changes motion. It alters speed or direction. It doesn't have to be present for motion to continue. This distinction is subtle but crucial, and it's one of the reasons motion seems so confusing when you first examine it closely. Once you internalize this, a lot of familiar situations start to look different. A car cruising at constant speed doesn't need a force to keep moving forward. It only needs a force to overcome drag and friction. A spacecraft coasting through space with its engines off is not doing anything special. It's just obeying the default behavior of motion in the absence of interference. Even standing still on Earth involves forces constantly acting to change motion. Gravity pulling you down, the ground pushing you up, internal muscular adjustments keeping you balanced. Stillness is not the absence of forces. It's the presence of forces arranged so that their effects cancel out. This reframing helps explain why motion never really ends. What ends is not motion itself, but our ability to track it as a single organized phenomenon. As energy spreads out, motion becomes fragmented across countless degrees of freedom. Instead of one object moving clearly in one direction, you get trillions of particles jostling randomly. The motion is still there, but it no longer adds up to something visually dramatic. From this perspective, the universe looks less like a collection of objects that move and stop, and more like a vast network of energy transfers, constantly reshaping how motion appears. What we call everyday motion is just the tip of that network, the part that happens to line up in ways our senses can follow. And this is where the conversation naturally drifts forward. Because once you accept that motion is not something that gets used up, the next question becomes unavoidable. If motion doesn't end, what exactly is it that's being conserved? What is this quantity that flows through systems, changes form, and refuses to disappear? To answer that, we have to look more carefully at what we mean by energy itself, not as a buzzword or a feeling, but as a precise concept that ties all of these observations together and explains why the universe never truly comes to rest. The The word energy is so familiar that it almost feels self-explanatory. We use it casually, constantly, and in wildly different contexts. We talk about having energy or lacking it. We hear about renewable energy drinks, energy bills, energy crises. In science, energy shows up everywhere too, in equations, in diagrams, in explanations for why things happen the way they do. Because it appears so often, it's easy to assume we all mean roughly the same thing when we use the word. But that assumption hides a problem. Energy is not an object, not a substance, not a single physical thing you can point to. It's an idea we use to describe something deeper, and until that idea is pinned down carefully, motion and change will always feel a bit slippery. One of the reasons energy is so hard to define cleanly is that it doesn't look like anything on its own. You never encounter pure energy sitting somewhere by itself. You encounter moving objects, warm surfaces, stretched springs, flowing currents, glowing light. Energy shows up through effects, not as a standalone entity. That makes it tempting to treat it as a vague cause, a kind of invisible fuel that powers events. But in physics, energy isn't a cause in that sense. It doesn't make things happen by itself. Instead, it's a way of keeping track of how systems can change and how those changes are related to one another. At its core, energy is a bookkeeping concept. That might sound underwhelming, but it's one of the most powerful bookkeeping systems ever devised. When physicists talk about energy, they're talking about a quantity that remains consistent across transformations. If one part of a system loses energy, another part gains it. If energy appears in one form, it disappears in another. The total stays the same. That consistency is what allows us to connect motion, heat, light, electricity, chemistry, and even biological processes under a single framework. This is why energy doesn't have a single, simple definition that fits into a sentence. Any short definition ends up being circular or incomplete. You'll often hear energy described as the ability to do work, which sounds reasonable until you try to unpack it. What counts as work? Why does the ability matter more than the action? And what about forms of energy that don't obviously do work in the everyday sense? The phrase isn't wrong, but it's not very illuminating on its own. It points in the right direction without explaining the terrain. A more useful way to think about energy is as a measure of how much change a system can undergo or cause without violating the underlying rules of physics. Change here doesn't mean anything dramatic. It could be as simple as an object changing speed, a substance changing temperature, or a chemical bond breaking and reforming. Energy quantifies how much of that change is possible and how it can be redistributed when interactions occur. This becomes clearer when you look at energy not as one thing, but as a family of related descriptions. Kinetic energy describes energy associated with motion. Thermal energy describes energy associated with random microscopic motion. Chemical energy describes energy stored in molecular structures. Electrical energy describes energy associated with charges and fields. Radiant energy describes energy carried by electromagnetic waves. None of these are separate substances. They're different ways of accounting for the same underlying quantity as it appears in different situations. What ties all of these together is conservation. No matter which form energy takes, the total amount in a closed system doesn't change. This isn't an assumption or a philosophical preference. It's an empirical observation that is held up across every experiment we've ever run. Whenever it looks like energy has been lost, a closer inspection reveals that it's been transferred or transformed, often into forms that are harder to track. This is where everyday language starts to get us into trouble. We say energy is used up or wasted, but that's never literally true. When a phone battery dies, the energy hasn't vanished. It's been converted into heat and other forms spread into the surroundings. When a car burns fuel, the chemical energy in the fuel is transformed into motion, heat, sound, and exhaust gases. None of it disappears. What changes is how concentrated and how useful that energy is for producing further organised motion. This distinction between energy existing and energy being useful is crucial. Energy can remain conserved while still becoming less available for doing the kinds of things we care about. That's why energy conservation doesn't mean we can recycle motion indefinitely without consequence. It means that while the total accounting never changes, the quality of the energy does. Organised motion tends to degrade into disorganised motion, and once it's spread out, gathering it back into a single purposeful form becomes extremely difficult. Understanding this helps clarify why energy is so closely tied to motion, without being identical to it. Motion is one way energy manifests, but it's not the only way. An object at rest can still possess energy. A compressed spring isn't moving, but it has the capacity to move things when released. A rock perched on a cliff isn't going anywhere, but it has gravitational energy relative to the ground below. Energy, in these cases, reflects potential for change, not change itself. This idea of potential often causes confusion because it feels abstract. How can something have energy if nothing is happening? The answer lies in relationships. Energy isn't an intrinsic property of an object in isolation. It depends on context. A rock has gravitational energy because of its position relative to Earth. A charged particle has electrical energy because of its interaction with an electric field. Change the context, and the energy accounting changes too. That relational nature of energy is one of its defining features. You can't assign an absolute amount of energy to an object without specifying the system it's part of and the reference points you're using. This is why different energy values can be calculated for the same object depending on the situation, without any contradiction. The physics still works because what matters are the differences and transfers, not the absolute numbers. Once you accept that energy is a way of tracking relationships and changes, its role in explaining motion becomes much clearer. Motion doesn't persist because objects are stubborn, or because something invisible keeps pushing them along. Motion persists because the energy associated with that motion has nowhere else to go unless interactions provide an outlet. In the absence of such interactions, energy remains tied up in motion, and motion continues. This also explains why energy shows up in systems that don't obviously involve movement. Heat, for example, is just motion at a scale too small and too chaotic for us to see directly. When an object cools down, it's not losing energy into nothingness. It's transferring energy to its surroundings through microscopic collisions and electromagnetic interactions. The motion is still there, just no longer organised into a single direction or pattern. Light behaves the same way. When a glowing object emits light, it's converting some of its internal energy into electromagnetic radiation. That radiation travels through space, carrying energy with it. When it's absorbed by another object, the energy doesn't vanish. It becomes heat, chemical change, or electrical excitation. The form shifts, but the accounting remains intact. One of the reasons energy is such a powerful concept is that it allows us to ignore a lot of unnecessary detail. Instead of tracking every force, every collision, every microscopic interaction, we can often get accurate predictions simply by following the energy. This doesn't mean the details don't matter. It means that energy conservation captures something fundamental about how all those details fit together. This is also why energy shows up so naturally in discussions about the future and the past. If you know how much energy is present and how it's distributed, you can often predict what kinds of changes are possible. A system with a lot of concentrated energy can undergo dramatic transformations. A system where energy is spread out evenly is far more constrained. Motion still exists in both cases, but its ability to organise itself into large-scale changes differs dramatically. Another subtle but important aspect of energy is that it's always defined with respect to some frame of reference. Motion energy depends on speed, and speed depends on who's doing the measuring. This doesn't break conservation laws because when reference frames change, the entire accounting shifts consistently. Energy conservation doesn't care about your point of view. It only cares that the total remains balanced within a given description. This flexibility is not a weakness. It's a feature. It allows energy to be applied across classical mechanics, relativity, and quantum physics without losing coherence. The specific forms and equations change, but the underlying principle remains recognizable. Energy continues to act as the thread that ties motion and change together across vastly different scales. It's also worth addressing a common misconception at this point. Energy is not synonymous with activity or excitement. A system can have a large amount of energy and appear completely still. Another system can be highly active, but involve very little energy overall. What matters is not how dramatic something looks, but how energy is stored and transferred within it. This is why small, fast-moving particles can carry enormous amounts of energy, and large, slow-moving objects can carry surprisingly little. It's also why a tiny temperature difference across a massive system can represent more energy than an intense but localized event. Our senses are not good judges of energy content. They evolved to handle survival-relevant scales, not to intuitively grasp physical accounting. As this idea settles in, motion starts to feel less like a special case and more like one expression of a broader pattern. Energy doesn't exist to create motion. Motion exists because energy can take that form. When conditions allow energy to organize itself into coordinated movement, motion appears. When conditions don't, energy still exists, but motion becomes less obvious. This perspective also dissolves the idea that motion needs a purpose or a driver. The universe doesn't move because it's trying to go somewhere. Motion happens because energy distributions change over time according to consistent rules. There's no goal, no endpoint built into the process. Motion doesn't need to end any more than energy needs to disappear. As we continue, this understanding of energy will serve as the foundation for everything that follows. It explains why motion persists, why it transforms, and why it often seems to fade even though it hasn't truly gone anywhere. With that foundation in place, the next step is to look backward, not in time but in understanding, to see how humans first tried to make sense of motion and energy long before they had the language or tools we use today. Because the struggle to understand motion didn't begin with equations. It began with hands, tools, and the simple act of trying to move heavy things from one place to another. Long before anyone spoke about energy, before equations, before diagrams, before even the idea that motion could be measured precisely, humans were already living inside a world shaped by movement. They pushed, pulled, lifted, carried, threw, dragged, and built, all without any formal theory of what made things move or why they stopped. Motion was not an abstract concept. It was physical effort. It was strain in the muscles, resistance under the hands, fatigue after work. Understanding motion began not as science but as experience. For most of human history, motion was inseparable from survival. Food had to be gathered or hunted, water had to be carried, shelter had to be built. Every task involved moving matter against resistance, and that resistance felt fundamental. Heavy things resisted being lifted. Rough ground resisted being crossed. Wind resisted forward progress. Nothing moved easily unless someone or something forced it to. From this perspective, it made perfect sense to believe that motion required continuous effort. Stop pushing, and the object stops moving. Stop rowing, and the boat slows. Stop walking, and you come to rest. Motion appeared to be something fragile, something that faded the moment attention or effort was withdrawn. This lived experience shaped early intuition in a powerful way. Motion was associated with life and activity. Stillness was associated with rest, completion, or even death. A moving animal was alive. A still one might not be. A flowing river was dynamic. A stagnant pool felt lifeless. These associations were practical and emotionally reinforced. They worked well enough to guide daily life, even if they didn't describe the deeper mechanics of the universe. Before machines, motion rarely existed without a visible source. Humans were the engines, animals were the engines. Wind and water were exceptions, but even they were seen as active agents, almost intentional forces that pushed and pulled objects along. A cart moved because an animal pulled it. A stone flew because a person threw it. A mill turned because water drove it. Motion always seemed to have a clear origin, and when that origin stopped acting, motion stopped too. What early humans didn't have was the concept of isolating motion from its surroundings. Everything moved within a thick web of interactions. Objects scraped along the ground. Air pressed against bodies. Materials bent, flexed, and absorbed impacts. There was no such thing as frictionless motion in everyday life. Because of this, it was impossible to observe motion continuing on its own for very long. The world constantly interfered. This interference became so familiar that it faded into the background of thought. Resistance was not seen as a separate effect. It was simply how the world behaved. If a rock stopped rolling, it was because rolling naturally ended. If a spear fell to the ground, it was because motion ran out. The idea that motion might continue indefinitely under different conditions never had a chance to develop, because those conditions were never encountered. Even tools and simple machines didn't immediately challenge this view. Levers, ramps, pullers, and wheels made tasks easier, but they didn't eliminate resistance. They redistributed effort, traded force for distance, or redirected motion. But everything still slowed down when the effort stopped. A wheel rolled farther than a block slid, but it still eventually came to rest. The improvement was obvious, but the underlying assumption remained unchanged. Motion still appeared temporary. What's important here is not that early humans were wrong, but that they were reasoning from a limited data set. Their conclusions were grounded in observation, not ignorance. Given the environment they lived in, the idea that motion required continuous input was reasonable. The mistake, if it can even be called that, was assuming that this behavior reflected a universal rule rather than a local condition. This perspective carried into early attempts at explanation. When people began to think systematically about nature, motion was treated as something that needed a cause not just to begin, but to continue. If an object moved, something must be acting on it. If nothing acted, motion would cease. This view became embedded in early natural philosophy because it matched daily experience so well. But even within that framework, cracks began to appear. Some motions didn't fit neatly into the idea of constant driving. Projectiles, for example, were puzzling. When a stone was thrown, it continued moving even after it left the hand. Something seemed to be carrying it forward. Early explanations often involved the surrounding air continuing to push the object along, or some internal quality imparted during the throw. These ideas weren't precise, but they reflected an intuitive struggle to explain why motion persisted even briefly without direct contact. Rotational motion posed similar challenges. A spinning top, once set in motion, could continue spinning for a surprisingly long time. It didn't require continuous pushing, only an initial impulse. Yet even here, motion eventually faded. The top slowed, wobbled, and fell over. Again, resistance quietly did its work, but without a clear concept of friction as an energy transfer mechanism. The slowdown looked like motion exhausting itself. Water offered another clue. Rivers flowed continuously without any visible pushing. They followed paths carved over long periods of time, reshaping landscapes through persistent motion. But even here, the motion was attributed to external causes. Gravity pulled water downhill. Rain replenished the source. The motion didn't appear self-sustaining. It was part of a cycle that required constant input. Wind behaved similarly. It moved objects without visible contact, which gave it an almost magical quality. But wind itself was explained through ideas of breath, spirits, or imbalance. Motion still had a cause, even if the cause was invisible or poorly understood. The absence of machines capable of sustained, isolated motion reinforced all of this. Before engines, before flywheels, before precision bearings, there was nothing in daily life that demonstrated motion persisting cleanly over long periods. Every example of motion was embedded in resistance and decay. Energy, though unnamed, was constantly leaking away into the environment. This shaped not only practical thinking, but language. Words for effort, work, and motion were intertwined. To move something was to labour. To stop moving was to rest. The idea that motion could exist without effort felt almost contradictory. Motion was something you did, not something that simply happened. Even time itself was often understood through motion. Days passed as the sun moved across the sky. Seasons changed as stars shifted position. Life progressed through cycles of activity and rest. Motion marked change, and change required cause. Stillness meant completion, equilibrium, or exhaustion. What's striking is how long this worldview remained dominant, not because people resisted new ideas, but because the world kept confirming it. Without controlled experiments or environments that reduced resistance, there was no obvious reason to question it. Motion seemed to run down naturally. The universe looked like a place where activity had to be maintained against an underlying tendency toward rest. Only much later would it become clear that this tendency was not a fundamental property of motion itself, but of the environments humans happen to inhabit. Earth is dense, it's full of matter, interactions are unavoidable. Motion here is constantly being redistributed into microscopic forms that are hard to notice. But that redistribution is not the same as destruction. Understanding motion before machines then means understanding a world where energy was always tied up in effort and loss. There was no clear separation between moving something and exhausting oneself. The idea that motion could be conserved, that it could persist without continuous input, had no obvious demonstration. It would take new tools, new ways of isolating systems, and new ways of thinking to reveal that what looked like an ending was really a transformation. As tools became more refined and systems more controlled, the assumptions built from everyday experience would begin to loosen. People would start to notice that motion behaved differently when resistance was reduced, when contact was minimized, when the environment interfered less. Those observations would eventually force a shift from thinking about motion as something that naturally dies out, to thinking about it as something that only changes when acted upon. But that shift didn't happen all at once. It emerged gradually, built on centuries of practical interaction with motion, long before the language of energy existed. And it's that slow transition from lived experience to formal understanding that sets the stage for the next step, where intuition gives way to principle and motion begins to be treated not just as effort, but as something that follows deeper, more universal rules. Long before motion was analysed, measured or formalised, it was interpreted. Humans didn't begin by asking what motion is in an abstract sense. They asked what it meant, why some things moved on their own while others had to be forced, why living things moved differently from stones, why the sky moved in patterns while the ground seemed fixed. These questions didn't arise in laboratories. They arose around fires, during travel, in work, in watching animals, weather, and the slow repetition of days and seasons. The ancient intuition of moving things was shaped by contrast. Some motion appeared purposeful. Animals moved with intent. Humans moved with goals. Wind moved unpredictably. Water flowed persistently. Fire flickered and spread. Other things moved only when acted upon. Rock stayed put unless pushed. Trees stood still unless bent by wind. Tools lay motionless until picked up. From this contrast came an early division that would influence thinking for centuries. The idea that motion had different kinds, some natural, some imposed. Living motion felt fundamentally different from non-living motion. Animals initiated movement without visible external force. They changed direction suddenly. They stopped and started at will. This gave rise to the idea that living things possessed an internal source of motion, something that inert matter lacked. Motion, in this view, was tied to vitality. To move was to be alive. To stop moving was to die. Even today, traces of this intuition remain in how we speak. We describe lively people as energetic. We describe inactivity as lifeless. Natural phenomena reinforce this idea. Rivers flowed endlessly. The sun crossed the sky every day. Stars traced repeating paths across the night. These motions were regular, predictable, and seemingly eternal. They did not require visible effort. They simply happened. By contrast, a stone thrown into the air followed a brief arc and then fell. Its motion was temporary, borrowed, and dependent on the throw. This difference suggested that some motions belonged to the structure of the world itself, while others were artificial disturbances that quickly faded. From this emerged the idea of natural motion. Objects, it was thought, had preferred states and preferred directions. Heavy things naturally moved downward. Light things rose. Fire went up. Earth went down. The heavens moved in circles. When objects behaved differently, it was because something interfered. A stone thrown upward was temporarily forced away from its natural tendency. Once the forcing ended, it returned to what it was meant to do. This way of thinking was not careless or naive. It was systematic, coherent, and grounded in observation. If you released a rock, it fell. If you released smoke, it rose. If you stopped pushing a cart, it slowed and stopped. Motion seemed to have directionality and purpose built into it. The world appeared ordered by tendencies rather than neutral laws. Within this framework, the persistence of motion was not the default. Rest was. Objects were thought to seek their natural place, and once they reached it, motion ceased. This made sense in a world dominated by gravity, friction, and resistance. On Earth, most things really do end up at rest relative to the ground. Without careful isolation, the idea that motion could continue indefinitely had no obvious support. The ancient intuition also treated space differently from how we do now. Space was not an empty stage. It was a filled environment, often imagined as layered or structured. The air, the earth, the heavens all had their own properties. Motion through these regions was influenced by their nature. Moving through air was different from moving through water. Moving near the ground was different from moving in the sky. Motion was contextual, shaped by where it occurred. This context-dependent view made it difficult to imagine universal rules of motion. If the behavior of moving objects depended on their nature and their surroundings, then there was no reason to expect a single principle to govern all motion. Instead, different things moved in different ways for different reasons. Understanding motion meant understanding the character of the object and the medium it moved through. The intuition extended to tools and weapons as well. A spear thrown farther was seen as having been given more force, more impetus, more something internal that gradually ran out. Motion was treated like a stored quality that dissipated over time. The idea that this something could be conserved or transferred invisibly did not arise naturally. When motion faded, it was assumed that the cause of motion had faded with it. Even circular motion, which later would become central to understanding inertia, was interpreted through this lens. The circular paths of celestial bodies were often seen as perfect and self-sustaining, fundamentally different from linear motion on Earth. Circles had no beginning or end. They returned to themselves. Linear motion, by contrast, had a clear start and finish. It went somewhere and then stopped. This reinforced the idea that earthly motion was temporary, while cosmic motion was eternal. This division between celestial and terrestrial motion persisted for a long time. The sky was governed by different rules than the ground. What happened above did not necessarily apply below. Motion in the heavens could be uniform and unending, while motion on Earth was messy, decaying, and tied to effort. This separation delayed the realization that the same principles govern both. What's important here is that ancient intuition was not blind to patterns. It noticed regularity, repetition, and consistency. It recognized that some motions repeated reliably and others did not, but it explained these observations in terms of purpose, tendency, and nature rather than conservation and transformation. Motion was something things did according to what they were. Because of this, stopping felt final. When a stone came to rest, it had reached its natural state. There was no reason to think anything about it continued. Any internal activity was invisible and irrelevant. Motion had ended. The idea that microscopic motion might persist even when macroscopic motion stopped was far beyond what intuition could support. The same applied to heat. Warmth was associated with fire, life, or sunlight. When something cooled down, it was thought to lose its heat as a substance. There was no concept of heat as motion. Cooling felt like energy leaving the object and disappearing. Again, everyday experience supported this view. Warmth faded. Coldness remained. Sound offered another example. A struck bell rang and then fell silent. The sound clearly moved through the air, but once it faded, it seemed gone. There was no obvious trace. The idea that the sound energy had dispersed into countless microscopic vibrations was not available. Silence looked like absence, not redistribution. These interpretations were reinforced culturally and philosophically. Motion was often associated with change, and change with imperfection. Stability was valued. Rest was completion. A finished structure stood still. A settled life was unmoving. Endless motion could even feel unsettling, a sign of disorder rather than balance. This worldview shaped early explanations not only of physics but of life, health, and the cosmos. Balance was achieved through stillness. Excess motion was instability. The goal was equilibrium, not persistence. In such a framework, the idea that motion never ends would have sounded not just wrong, but conceptually incoherent. And yet, even within this intuition, there were hints of something deeper. Some motions did not fit neatly into the idea of natural rest. Spinning objects resisted stopping more than sliding ones. Smooth surfaces allowed motion to persist longer. Objects in water behaved differently than objects on land. These inconsistencies didn't immediately overturn the prevailing view, but they planted seeds of doubt. The ancient intuition was powerful because it worked most of the time. It allowed people to predict behavior well enough to build, hunt, travel, and survive. It didn't need to be universally true to be useful. It only needed to be good enough within the constraints of daily life. But usefulness is not the same as fundamental truth. As tools improved and environments became more controlled, the limits of this intuition would become more apparent. When resistance was reduced, motion behaved less like something that naturally died out, and more like something that simply continued. The distinction between cause and change began to sharpen. Motion started to look less like a quality that objects possessed and more like a state they occupied. This transition didn't happen because ancient thinkers were careless or wrong. It happened because intuition is shaped by conditions. Change the conditions and intuition must adapt. The ancient understanding of motion was a product of a world thick with resistance, where energy was always bleeding away into the surroundings. It made motion feel temporary and effort-bound. What would eventually challenge this intuition was not philosophy alone, but experience. Experience with smoother surfaces, rotating devices, controlled experiments, and eventually machines that could isolate motion from its usual losses. Those developments would force a re-evaluation of what motion really was, stripping away the idea that it naturally sought rest and replacing it with something far more unsettling and far more powerful. Because once motion was no longer tied to effort or intention, once it was seen as something that did not need to be sustained, the entire picture of how the world worked had to change, and that change would begin not with abstract reasoning, but with simple observations that contradicted what intuition had always insisted was true. The shift from seeing motion as something driven by pushes to understanding it as something governed by principles did not happen suddenly, and it did not begin with equations. It began with discomfort, discomfort with explanations that worked well enough in daily life but failed when examined closely. As tools improved and observations became more careful, the old intuition that motion required constant effort started to feel strained. Certain behaviours refused to fit neatly into the idea that movement naturally ran out on its own. At first, these tensions appeared in practical context rather than theoretical ones. Builders noticed that smoother surfaces allowed objects to move farther with the same effort. Artisans working with rotating tools observed that once spinning, these tools resisted stopping more than expected. Soldiers throwing projectiles learned through experience that angle and speed mattered in predictable ways, even if the reasons were unclear. Sailors learned to work with wind and water, noticing that motion persisted differently depending on conditions. None of this overturned the prevailing view by itself, but it introduced cracks. The idea that motion was sustained by continuous pushing began to look less universal and more conditional. When resistance was reduced, motion behaved differently. It lasted longer. It followed cleaner paths. It became easier to predict. This suggested that something about the environment, not motion itself, was responsible for the apparent tendency toward rest. What made this realization difficult to articulate was the lack of separation between cause and effect in everyday thinking. When someone pushed an object and it moved, it was natural to assume the pushing caused the movement and continued to cause it for as long as the object was in motion. The idea that the push merely changed the state of the object, rather than sustaining it, was subtle. It required rethinking what forces actually do. Forces feel like active agents. You feel them in your muscles, you see their effects immediately. But feeling a force does not tell you how motion behaves in its absence. As long as every familiar example of motion involved resistance, there was no clear reason to suspect that motion itself might be neutral, neither fading nor growing unless something intervened. The turning point came from paying attention to what changed when conditions changed. When surfaces became smoother, objects slid farther. When bearings improved, rotation persisted longer. When air resistance was reduced, motion became more uniform. These patterns hinted at something deeper. If motion naturally sought rest, reducing resistance should not fundamentally alter that tendency. And yet, it did. Gradually, a different picture began to emerge. Motion did not need to be explained as something constantly fed by force. Instead, force could be understood as something that altered motion. A push did not create motion in the sense of bringing something into existence. It changed how something moved. It modified speed or direction. Once that change occurred, the motion itself did not require further explanation unless another interaction took place. This distinction sounds simple when stated plainly, but it represents a profound conceptual shift. It separates the initiation of motion from its continuation. It treats motion as a state rather than an activity that consumes a resource. In this view, an object in motion is not actively doing something that needs to be sustained. It is simply continuing in a condition it already occupies. Making this shift required abandoning the idea that rest was the natural default. Instead, rest became just one possible state among many, no more fundamental than uniform motion. What determined whether an object changed its state was not an internal tendency, but external interaction. This new way of thinking allowed for generalization. Instead of different rules for different kinds of motion, it suggested a single principle governing all of them. Whether an object was sliding, rolling, spinning, or flying, its motion followed the same basic pattern. Changes occurred only when something interfered. At this stage, explanation began to move away from stories about purpose or nature and towards statements about consistency. Motion was no longer something that happened because an object wanted to move or had been imbued with a quality that was gradually used up. It happened because energy and momentum were redistributed through interactions in reliable ways. What made principles so powerful compared to pushes was their independence from specific situations. A push is an event. It happens at a particular time and place. A principle applies everywhere, all the time, regardless of scale or context. Once motion was framed in terms of principles, it became possible to connect very different phenomena under the same description. This also clarified why earlier explanations had struggled with projectiles. When a stone left the hand, there was no need to invent an invisible force carrying it forward. The stone simply continued in the state it had been given, until gravity and air resistance altered that state. The mystery dissolved once the assumption that motion needed continuous support was removed. Rotation, too, became easier to understand. A spinning object did not keep spinning because it possessed some special circular tendency. It kept spinning because nothing was acting strongly enough to change that motion. The resistance it encountered gradually transferred its energy into other forms, slowing the rotation, but the motion itself was not decaying by nature. It was being altered by interaction. This rethinking also forced a more careful examination of stillness. Standing still was no longer the absence of motion, but a balance of influences. An object at rest was not doing nothing. It was being held in a stable state by forces that cancelled out. Gravity pulled downward, a surface pushed upward, internal stresses balanced. Rest was active equilibrium, not default inactivity. As these ideas solidified, the language used to describe motion began to change. Instead of asking what caused motion, thinkers began asking what caused changes in motion. Instead of treating force as something that maintained movement, it became something that redirected or reshaped it. This subtle shift in emphasis opened the door to more precise reasoning. With principles in place, it became possible to predict behavior beyond familiar situations. If motion persisted unless altered, then objects in environments with very little resistance should behave in ways that everyday intuition did not expect. This prediction could be tested. When it was, the results supported the principle, not the intuition. Importantly, this shift did not eliminate the role of forces or effort in everyday life. It reinterpreted them. Pushing a heavy object still required work. That work still had a cost, but the cost was no longer explained as sustaining motion against an inherent tendency toward rest. It was explained as overcoming resistance and transferring energy into the object. This distinction mattered because it clarified why energy accounting always balanced. The work done by a push did not vanish when motion ceased. It showed up as heat, sound, deformation, and microscopic motion. Motion did not end because its energy ran out. It ended because that energy had been redistributed into forms that no longer produced visible movement. Principles also allowed motion to be separated from intention. The universe did not need to want anything. Objects did not need goals or preferences. Motion followed rules because the structure of interactions enforced them, not because anything was trying to reach an endpoint. This shift away from intention was difficult culturally as well as intellectually. Humans naturally interpret the world in terms of agency. We are accustomed to explaining behavior by reference to desires and purposes. Removing those explanations from physics felt unnatural at first, but doing so made the explanations far more robust. Once principles replaced pushes as the foundation of understanding, motion could be studied independently of specific materials or situations. The same descriptions applied to stones, planets, fluids, and later even to light and particles. The idea that the universe followed consistent rules regardless of scale began to take hold. This consistency also made it possible to see energy as a unifying concept, rather than a collection of separate effects. If motion persisted unless altered, then the question shifted to what altered it and how. Energy provided the answer. It quantified the capacity for change and tracked how motion transformed as interactions occurred. The move from pushes to principles did not eliminate mystery. It reframed it. Instead of wondering why motion needed to be sustained, the deeper question became why interactions behaved the way they did, and why energy was conserved across them. These questions were harder, but they were also more precise. This reframing also prepared the ground for understanding motion at scales far removed from human experience. Celestial motion no longer required special rules. It followed the same principles as terrestrial motion. The heavens were not governed by a different logic. They simply existed in an environment with far less resistance. As these ideas spread, the picture of the universe changed. It no longer looked like a place where motion was constantly being created and destroyed. It looked like a place where motion was continuously reshaped. The emphasis shifted from endings to transformations. What had once seemed like obvious truths revealed themselves as assumptions built from limited experience. Motion did not naturally fade. It was damped by interactions. Rest was not the preferred state of matter. It was one possible outcome among many. This change in perspective was not just a technical improvement. It altered how time, change, and causality were understood. If motion could persist indefinitely, then the universe was not running down in the way intuition suggested. It was evolving through redistribution, not exhaustion. That realization made it possible to ask new questions. If motion persisted, how was it stored? If it transformed, what governed those transformations? If it spread out, could it ever be gathered again? These questions would lead directly to more formal statements about inertia, energy conservation, and eventually the deeper laws that govern physical systems. The transition from pushes to principles did not end the investigation into motion. It made it possible. It replaced stories with structures and intuition with consistency. And once motion was understood as something that did not need to be sustained, the idea that it might never truly end stopped sounding radical and started sounding inevitable. When Isaac Newton began to formalize his ideas about motion, he wasn't trying to overturn common sense. In many ways, he was trying to rescue it. Everyday experience gave people reliable expectations about how objects behaved, but those expectations were tangled together with assumptions that didn't always hold up. Newton's contribution was not that he invented motion out of thin air, but that he stripped away the parts of intuition that came from living in a world full of resistance and replaced them with principles that still worked when resistance was removed. The most radical of these principles sounded almost trivial once stated plainly. Motion does not need a reason to continue. An object that is already moving will keep moving in the same way unless something acts on it. Likewise, an object at rest will remain at rest unless something interferes. This idea, now known as inertia, marked a clean break from centuries of thinking that treated motion as something that had to be continuously sustained. What made this idea so unsettling was not that it contradicted observation, but that it reinterpreted observation. People had always seen objects slow down and stop. What Newton insisted on was that this behaviour did not reveal the true nature of motion. It revealed the presence of forces that interfered with it. Friction, air resistance, internal deformation, all of these effects were responsible for changing motion, not motion itself. In Newton's world, motion did not want to stop. It didn't want anything at all. Motion simply persisted. Change was the exception, not the rule. If an object sped up, slowed down, or changed direction, that change demanded an explanation. Uniform motion did not. This flipped the burden of explanation entirely. Instead of asking why something kept moving, physics began asking why it ever changed how it moved. That question turned out to be far more productive. To understand how profound this shift was, it helps to separate two ideas that everyday language often blends together: motion and force. Before Newton, force was often imagined as something that directly produced motion. Push harder, get more motion. Stop pushing, motion fades. Newton reframed force as something that produces acceleration, not motion itself. Acceleration here means any change in motion, whether that's a change in speed or direction. This distinction matters because it means that motion itself is not fragile. It doesn't need to be constantly replenished. It only changes when forces act. In a perfectly isolated system, motion would continue forever without alteration. Of course, such isolation doesn't exist in daily life. On Earth, objects are always interacting with their environment. But Newton's genius was recognizing that these interactions were not fundamental to motion. They were contingent. Remove them, and motion reveals its true character. This insight allowed Newton to unify terrestrial and celestial motion under the same framework. The same principle that described a rolling ball could describe a planet orbiting the sun. There was no need for separate rules for the heavens and the earth. Motion was motion everywhere. In Newton's picture, the universe became a vast system of objects moving through space and time, each following simple rules unless acted upon. Space was a stage. Time flowed uniformly. Objects moved in straight lines at constant speeds unless forces intervened. Forces, in turn, arose from interactions between objects, such as gravity or contact. This view made motion predictable in a way it had never been before. If you knew the forces acting on an object, you could calculate how its motion would change. If no forces acted, you didn't need to calculate anything at all. The motion would simply continue. The law of inertia also clarified why motion seemed to fade in everyday situations. When a sliding object slows down, it's not because motion is being used up. It's because friction is acting on it, transferring energy into microscopic motion in the surfaces and the surrounding air. The object's motion changes because a force is acting on it continuously. Once this was understood, stillness itself took on a new meaning. An object at rest was no longer seen as being in a special, natural state. It was simply in a state of zero velocity relative to a chosen frame of reference. That state required explanation only if it changed. This reframing made rest symmetrical with motion. Both were just states. Neither was more natural than the other. What mattered was whether the state persisted or changed. This symmetry had enormous consequences. It meant there was no preferred state of motion in the universe, no cosmic reference point that defined true rest. Motion was always relative. An object could be at rest in one frame of reference and moving in another, with no contradiction. The laws of motion work the same either way. This idea eroded the last traces of the ancient belief that motion had intrinsic tendencies. Objects did not seek rest. They did not seek motion. They simply persisted in whatever state they were in until something happened to change that state. Newton's framework also clarified the role of energy, even though he did not use the modern concept in the way we do today. When forces acted on objects, they transferred energy. When no forces acted, energy associated with motion remained tied up in that motion. It did not decay on its own. This explains why a spacecraft coasting through space does not slow down. There is no friction to drain its energy. There is nothing to interfere with its motion. In Newton's world, this behavior is not surprising or exotic. It is the default. It also explains why machines that reduce friction can sustain motion longer. A flywheel spins longer than a sliding block because it loses energy more slowly. Not because rotation is special, but because the pathways for energy transfer are fewer. One of the most subtle implications of inertia is that it makes motion timeless in a certain sense. If nothing interferes, nothing changes. Motion does not age. It does not wear out. It does not need maintenance. Time can pass without altering the state of motion at all. This idea challenges the intuitive link between time and decay. In everyday experience, things change as time passes. Objects wear down, motion fades. But in Newton's framework, time alone does nothing. Change requires interaction. Time is a parameter, not a cause. This distinction is crucial for understanding why motion never truly ends. Motion only changes when energy is transferred. If energy remains bound up in motion and no interactions occur, there is nothing to bring that motion to an end. Newton's laws also made it possible to distinguish clearly between motion that looks complex and motion that actually is complex. A planet's orbit looks intricate. but it follows a simple rule. It moves in such a way that its inertia and gravitational interaction balance. A spinning top looks stable, but its stability arises from the persistence of angular motion. Once these patterns were recognized, motion stopped being mysterious in the old sense. It became something that could be described, predicted, and understood without appealing to purpose or exhaustion. Importantly, Newton's world was not a denial of everyday experience. It explained it. Friction, drag, and resistance were not illusions. They were forces. They had causes. They transferred energy. They changed motion. They simply weren't fundamental properties of motion itself. This made it possible to see the everyday world as a special case, not the general rule. Earth is a noisy environment. It is full of interactions. Motion here is constantly being reshaped, but that reshaping hides the deeper simplicity underneath. In Newton's framework, the universe does not grind to a halt unless something causes it to. Motion is not a flame that burns out. It is a condition that persists. This realization also reframed human effort. When you push something, you're not feeding motion into it moment by moment. You're changing its state by transferring energy. Once that transfer is complete, the motion carries on according to the same rules as everything else. That perspective removes drama from motion. There is no struggle between movement and stillness. There is only continuity interrupted by interaction. As powerful as Newton's ideas were, they did not answer every question. They described how motion behaved, not why the universe was structured in a way that allowed these principles to hold. They treated space and time as fixed backgrounds rather than dynamic participants. Those limitations would matter later, but within its domain, Newton's world revealed something essential. Motion is not something that needs encouragement. It does not run down by itself. It does not prefer rest. It continues. Once that idea is accepted, the phrase motion never ends stops sounding poetic and starts sounding literal. Motion ends only when it is transformed. It ends only when energy moves elsewhere. And even then, it has not disappeared. It has simply changed where and how it shows up. From this point onward, understanding motion becomes inseparable from understanding how energy moves through systems, how it spreads, and how it resists being destroyed. Newton gave us the stage where motion could persist. What remained was to understand what happens to motion when it appears to fade, and why that fading is never as final as it seems. Motion doesn't always announce itself. Sometimes it hides. Sometimes it waits. One of the most important shifts in understanding why motion never truly ends comes from realizing that movement doesn't have to be happening right now to matter. Energy can exist without visible motion, stored in arrangements, positions, and structures, ready to be released when conditions change. This quiet presence of stored energy is easy to overlook precisely because nothing appears to be happening. And yet, it plays a central role in how motion persists through time. Everyday experience encourages us to equate motion with activity. If something isn't moving, it feels inactive. A stretched rubber band sitting on a table looks calm. A book resting on a shelf looks inert. A rock balanced on a ledge appears completely still. But in each of these cases, the absence of visible motion is misleading. These systems are not empty of energy. They are holding it in reserve, constrained by their configuration and their surroundings. This idea is often summarized by the term potential energy, but that label can be deceptive. It can make stored energy sound hypothetical or unreal, as if it only exists in the future when motion finally happens. In reality, stored energy is just as real as kinetic energy. It contributes to the behavior of systems right now, even if nothing is visibly changing. Consider a compressed spring. It sits quietly, not moving, not vibrating in any obvious way, and yet it resists further compression. It pushes outward against whatever is holding it in place. That resistance is not imaginary. It reflects real forces arising from the arrangement of atoms inside the material. energy has been transferred into the spring by compressing it, and that energy remains there as long as the spring shape is constrained. If the constraint is removed, the stored energy doesn't need to be created anew. It doesn't need to be coaxed into existence. It simply changes form. The spring expands, motion appears. Energy that was stored as internal stress becomes energy of motion, sound, and heat. Nothing new has been added. Nothing has been lost. Motion emerges not because energy was created, but because it was allowed to reorganize. The same logic applies to objects held at height. A book resting on a shelf is not moving, but it is part of a gravitational relationship with the Earth. That relationship has consequences. The book presses down on the shelf. The shelf presses up on the book. Forces are balanced, but energy is present in the system because of the book's position. If the shelf fails, the book doesn't suddenly acquire energy from nowhere. It converts stored energy associated with its position into motion as it falls. This positional energy feels intuitive in hindsight, but it wasn't always obvious. For a long time, energy was associated primarily with motion itself. Stillness was equated with absence. It took careful reasoning to recognize that energy could be present without visible movement, shaping what would happen next. This recognition is crucial for understanding why motion never truly ends. Motion can pause at the macroscopic level without energy disappearing. When motion seems to stop, it often means energy has been temporarily locked into a configuration, rather than dissipated completely. That energy can remain available, sometimes for very long periods. Chemical energy provides another example. A piece of wood sitting on the ground is not moving. It looks passive, but its molecular structure contains stored energy resulting from chemical bonds. That energy was not created by the wood itself. It was stored through a chain of processes involving sunlight, photosynthesis, and growth. As long as the wood remains intact, that energy stays locked into its structure. When the wood burns, the stored energy is released. It becomes heat, light, expanding gases, and motion in the surrounding air. The fire does not conjure energy from nothing. It unlocks energy that was already present, reorganizing it into forms that are hard to ignore. What's important here is that energy storage does not freeze energy in time. Stored energy is not static in the way a stopped clock is static. It exists within systems that are constantly interacting at microscopic scales. Atoms vibrate. Electrons shift. Forces remain active. The system is dynamic even when the overall configuration looks unchanged. This challenges the everyday idea that motion must always be visible to be meaningful. In reality, visible motion is just one expression of energy flow. Stored energy is another, equally important one. Without it, the universe would behave very differently. Motion would have no memory. Every event would require continuous input. Nothing could build up, wait, or be released later. The ability to store energy is what allows systems to accumulate change over time. It allows motion to be deferred rather than eliminated. A dam holds back water, storing energy that can later be converted into motion through turbines. A battery stores energy in chemical form, ready to drive electrical currents. Muscles store energy in molecular arrangements that can be rapidly converted into movement. In all of these cases, motion appears in bursts rather than continuously, but the underlying energy flow never stops. It simply alternates between visible and hidden forms. This alternation explains why the world doesn't grind to a halt between actions. When you stop walking, the energy that powered your movement doesn't vanish. Some of it dissipates as heat. Some of it remains stored in your body as chemical energy, ready for the next movement. The continuity of energy is what allows motion to resume without starting from nothing. It also explains why systems can appear stable for long periods without violating the idea that motion never ends. A mountain range can stand for millions of years. A planet can orbit for billions. A chemical compound can persist indefinitely under the right conditions. Stability does not mean inactivity. It means that energy flows are balanced in a way that maintains a configuration. Even structures that look completely rigid rely on stored energy. The strength of a bridge comes from internal forces within its materials, forces that arise from atomic interactions holding structures together. Those forces reflect energy stored in bonds and arrangements. Without that stored energy, the structure would collapse. Motion would appear suddenly as gravity reasserted itself. This perspective also clarifies why breaking things releases energy. When bonds are broken, the energy that held those bonds in place doesn't disappear. It changes form. It becomes motion, heat, sound, deformation. Destruction is not the annihilation of energy. It is a redistribution. One of the most subtle aspects of stored energy is that it depends on reference points and context. Energy stored in position depends on what you consider down. Energy stored in a stretched spring depends on how far it is stretched relative to its natural length. There is no absolute storage independent of relationships. Energy exists within systems, not in isolation. This relational nature can make stored energy feel less tangible, but it's precisely what allows it to be so versatile. Because energy is tied to configuration, changing the configuration changes how energy can move. This is why motion can be redirected, delayed, or transformed without violating conservation. From the perspective of motion never ending, stored energy acts like a pause rather than a stop. It's motion waiting for permission. When conditions change, when constraints are removed or altered, stored energy finds new pathways to express itself. Motion resumes, often suddenly, sometimes violently, sometimes gently. This also explains why the same amount of energy can produce very different outcomes depending on how it is stored. A small amount of energy stored in a rigid structure can produce a sudden release when that structure fails. A larger amount of energy spread evenly may produce no noticeable motion at all. The form matters as much as the quantity. As understanding of stored energy deepened, it became clear that energy conservation did not imply perpetual visible motion. Instead, it implied perpetual availability. Energy could move between motion, storage, heat, radiation, and back again. Motion could disappear from sight without leaving the system. This realization softened the apparent conflict between inertia and everyday experience. Objects didn't contradict inertia by coming to rest. They complied with it while interacting with the environments that allowed energy to be stored and dissipated in complex ways. Motion ended locally, temporarily, but not fundamentally. The quiet power of stored energy is what makes the universe flexible. It allows motion to be reshaped across time. It allows systems to remember past interactions. It allows cause and effect to stretch beyond immediate contact. Without stored energy, the universe would be either frozen or chaotic. Nothing could accumulate. Nothing could wait. Everything would happen at once or not at all. The persistence of motion would be trivial because nothing could interrupt it meaningfully. Instead, motion weaves in and out of visibility, guided by storage and release. Energy hides in structures, in positions, in relationships, and then re-emerges as movement when circumstances permit. As we continue, this idea becomes even more important when we consider why motion so often seems to fade away permanently. If energy is conserved and motion can be stored, why does so much motion appear to be lost? Why do moving systems settle into states where visible motion no longer returns on its own? To answer that, we have to look at where stored energy goes when it spreads too thin, and why some forms of motion are easier to recover than others. That path leads directly into the role of heat, friction, and the processes that make motion appear to dissolve into stillness, even though at a deeper level it never truly does. When motion appears to end, heat is almost always involved. Not dramatic heat, not flames or glowing surfaces, but subtle warmth that spreads quietly and goes unnoticed. This is where the illusion of loss takes hold. Motion fades, nothing obvious replaces it, and it feels natural to conclude that something has vanished. In reality, motion has not been destroyed. It has been dismantled and redistributed into forms that no longer resemble the original movement in any simple way. Friction sits at the center of this process. It is one of the most familiar forces in everyday life, and yet one of the most misunderstood. Friction is often described as something that opposes motion, something that slows things down and brings them to rest. That description is accurate but incomplete. Friction does not remove motion from the universe, it redirects it, breaking organized movement into countless microscopic motions that spread outward into the surrounding environment. When you slide your hand across a table, you feel resistance. That resistance is friction. The motion of your hand does not simply stop at the surface. Instead, the atoms in your skin interact with the atoms in the table. Tiny bumps and irregularities catch and release. Chemical bonds stretch and relax. Electrons shift. Energy flows into vibrations within both materials. Those vibrations are heat. Nothing about this process involves disappearance. Energy is transferred from large-scale motion that you can see into small-scale motion that you cannot. The system becomes more active at the microscopic level, even as it appears calmer at the macroscopic level. This is why friction is so effective at hiding motion. Organized motion, like a sliding object or a spinning wheel, is easy to track. Disorganized motion, like trillions of atoms vibrating randomly, is not. To our senses, random motion looks like stillness. We cannot see it. We cannot follow it. We can only detect it indirectly through temperature changes. Heat, then, is not something separate from motion. It is motion. Specifically, it is motion that has lost coordination. Instead of many particles moving together in the same direction, they move independently, colliding, bouncing, and transferring energy constantly. The energy is still there, it is just spread out. This spreading is what gives rise to the feeling of irreversibility. Once energy has been converted into heat and distributed across a large number of particles, gathering it back into a single, organized motion becomes extremely difficult. Not impossible in principle, but overwhelmingly unlikely in practice. This is why motion appears to end for good. Consider a bouncing ball. Each time it hits the ground, it rebounds to a lower height. Eventually, it stops bouncing altogether. It feels like the energy of motion has been used up. But if you trace what happens at each impact, a different picture emerges. The ball deforms, the ground deforms. Sound waves travel outward. Heat spreads through both materials. The energy that once carried the ball upward is now shared among countless microscopic degrees of freedom. To reverse this process, all of those tiny motions would have to realign in just the right way, transferring their energy back into the ball in a coordinated upward motion. The laws of physics do not forbid this, but the probability is so small that it effectively never happens. This is not because energy is gone, it is because it is too evenly spread. This distinction between impossible and overwhelmingly unlikely is crucial. Physics does not say that motion cannot reappear from heat. It says that systems naturally evolve towards states where energy is more evenly distributed. Once that happens, spontaneous reorganization into large-scale motion becomes vanishingly rare. This is where the illusion of loss becomes convincing. In everyday life, motion that turns into heat does not come back. A sliding object stops, a spinning wheel slows, a stirred liquid settles. The final state looks calm and inactive. It feels like an ending. But at the microscopic level, the system is more active than before. Particles move faster, vibrations increase, energy continues to flow, colliding, exchanging, spreading outward into the environment. The universe has not become quieter, it has become noisier in a way we cannot easily perceive. Friction is not the only pathway for this transformation, but it is the most familiar. Air resistance works in the same way. As an object moves through air, it collides with air molecules. Those molecules gain kinetic energy. They move faster, collide with other molecules, and spread that energy further. The object slows, the air warms slightly. Motion has not been removed, it has been shared. Sound behaves similarly. When an object vibrates, it sets surrounding air into motion. That motion propagates as sound waves. As the waves travel, they spread out and weaken. Eventually, their energy becomes part of the random thermal motion of the air. The sound fades into silence, but the energy remains. Even light, when absorbed, follows this pattern. A surface absorbs light energy. Electrons are excited. Those excitations decay into vibrations and heat. The light disappears, but its energy becomes part of the thermal motion of the material. What all of these processes have in common is not loss, but dilution. Energy spreads out into more places, across more particles, and into more degrees of freedom. The more spread out energy becomes, the less capable it is of producing large organized motion. This spreading has a direction. Energy tends to flow from concentrated forms to dispersed forms. This is not a rule imposed from outside. It is a statistical tendency that arises from the sheer number of ways energy can be distributed. There are vastly more ways for energy to be spread out evenly than for it to be concentrated in a single coherent motion. Because of this imbalance, systems naturally evolve towards states of higher disorder. Motion becomes less coordinated. Energy becomes harder to harness. From our perspective, motion ends. But it has not ended. It has changed character. This is why heat is so central to understanding why motion never truly ends. Heat is motion that has become too fragmented to be useful for doing obvious work. It is not dead energy. It is busy energy. It is energy moving in all directions at once. The fact that we cannot easily convert heat back into organized motion does not mean the energy is gone. It means the pathway back is narrow. Engines and heat pumps exploit such pathways, but they always face limits. They cannot extract all the energy from heat. Some of it always remains spread out. This is not a failure of technology. It is a reflection of how probability shapes physical processes. There are many ways to go from order to disorder, and very few ways to go back. This is also why friction feels like an enemy of motion. It relentlessly converts visible movement into invisible activity. But friction is not a destroyer. It is a transformer. It moves energy from forms we can track into forms we cannot. Understanding this dissolves a common misconception about energy loss. Energy is never lost. What is lost is our ability to use it in simple, directed ways. The universe keeps the books balanced, but it does not promise convenience. This perspective also explains why perpetual motion machines fail. Not because motion must end, but because extracting work inevitably involves transferring energy into less organized forms. Each cycle spreads energy a little more. Eventually, there is not enough concentrated energy left to sustain the process in the same way. The illusion of loss is reinforced by time. As energy spreads, it mixes with the environment. Heat diffuses, sound dissipates, motion becomes part of a larger system. Tracking it becomes impractical. The energy is still there, but it is no longer associated with a specific object or event. This diffusion creates the sense that the past is gone. The motion that once existed is no longer recoverable in its original form. But irrecoverable is not the same as non-existent. The universe remembers motion in a different way. It remembers it as a change in overall energy distribution. That memory is written into the microscopic state of matter and radiation, not into visible movement. From this point of view, stopping is not an endpoint. It is a transition. Motion does not end at the moment an object comes to rest. It continues in the form of heat spreading through materials, air, and eventually into the wider environment. This is why even the quietest room is not truly still. The air is full of thermal motion. The walls vibrate at microscopic scales. Radiation passes through continuously. Motion is everywhere, just not organized into patterns we label as movement. Recognizing this helps explain why motion never ends, even though it so often appears to. What ends is coordination. What ends is visibility. What ends is usefulness for certain purposes. As we move forward, this understanding becomes even more important when we look at energy conservation more formally. If motion can dissolve into heat without disappearing, then there must be a deeper rule governing these transformations, a rule that guarantees that the accounting always balances even when the outcomes look like losses. That rule does not arise from intuition or experience alone. It emerges from a deeper principle that reshaped physics entirely, one that makes the persistence of motion not just an observation, but a necessity. There is a point in the story of motion where observation turns into inevitability, where patterns become so consistent that they stop feeling like habits of nature and start feeling like rules it cannot break. The conservation of energy is one of those rules. It does not describe a particular kind of motion or a specific force or a narrow class of systems. It describes something far more general. It states that no matter what happens inside a closed system, the total amount of energy remains the same. Energy can move, shift, spread, concentrate, hide, and reappear, but it cannot be created from nothing, and it cannot vanish into nothing. This idea did not arrive fully formed. It emerged slowly, pieced together from many different observations that at first seemed unrelated. Motion turning into heat, chemical reactions producing light and movement, electrical currents generating warmth, mechanical work disappearing in ways that always seem to leave behind the same amount of heating. Again and again, careful measurement revealed the same pattern. Whenever energy seemed to be lost, it reappeared somewhere else in a different form. What made this realization transformative was not just that energy was conserved in specific cases, but that it was conserved in all cases anyone could test. No exceptions emerged, no hidden drains, no mysterious leaks. The universe kept perfect accounts, even when humans struggled to track them. Before this principle was recognized, it was reasonable to believe that motion faded because the energy behind it was consumed. After all, effort feels exhausting. Machines wear down. Fuel runs out. From the human point of view, loss feels fundamental. But conservation of energy revealed that exhaustion and depletion are local experiences, not universal truths. They reflect the limits of specific systems, not the disappearance of energy itself. When a person grows tired, the energy that powered their movement has not vanished. It has been converted into heat, dispersed through their body and into the environment. When fuel is burned, the energy locked in chemical bonds is not destroyed. It becomes motion, heat, light, and sound. The fuel is gone, but the energy remains. This distinction matters because it breaks the intuitive link between endings and annihilation. Motion can end in one place and continue elsewhere. Energy can leave a system and enter another. What looks like an ending from one perspective is a continuation from another. The conservation of energy also forces a rethinking of causality. Events do not happen because energy appears when needed. They happen because energy already present is rearranged. Nothing gets a free pass. Every movement, every change, every transformation must draw from energy that was already there in some form. This is why the principle feels so absolute. It does not depend on the type of system. It does not depend on scale. It applies to falling objects, flowing rivers, chemical reactions, electrical circuits, biological metabolism, and stellar evolution alike. Wherever change occurs, energy is involved, and wherever energy is involved, the accounting balances. One of the most powerful aspects of this law is that it does not care about the details of how energy changes form. It does not matter whether energy moves through friction, radiation, chemical bonds, or gravitational interaction. The pathway can be complex or simple. The outcome can be dramatic or subtle. The total remains the same. This universality is what makes conservation of energy more than a useful guideline. It makes it a constraint on reality itself. Processes that would violate it simply do not occur. Designs that depend on creating energy from nothing fail every time, not because engineers lack creativity, but because the universe does not permit such behavior. From the perspective of motion never ending, this law is decisive. If energy cannot be destroyed, then motion, as one form of energy, cannot simply cease to exist. It can stop being organized, it can stop being visible, it can stop being recoverable in a useful way, but it cannot be erased. This reframes all of the familiar stories about motion stopping. A car comes to rest, a pendulum slows, a wave dies out. In each case, energy conservation insists that nothing has been lost. The motion energy has flowed into other forms, mostly heat, sometimes sound, sometimes deformation. The original motion is gone, but the energy that defined it has merely changed address. This also explains why motion can feel irreversible even though energy is conserved. Conservation does not guarantee reversibility. It guarantees balance. Once energy is spread into many degrees of freedom, reversing that spread becomes statistically improbable. The law does not promise that motion will return. It promises that motion has not been annihilated. Another way to see this is to consider how energy bookkeeping works in practice. You do not need to know every microscopic detail of a system to apply conservation of energy. You only need to account for energy entering and leaving. If the numbers do not add up, something has been missed. Either an interaction has been overlooked, or energy has been transferred in a way that was not recognized. This makes conservation of energy an extraordinarily powerful diagnostic tool. It allows physicists to infer unseen processes. If energy disappears from one place, it must appear somewhere else. If it cannot be found, the theory is incomplete. This principle has driven discovery as much as it has explained known phenomena. Entire fields of physics have developed because energy accounting demanded something new. Invisible radiation, internal molecular motion, nuclear binding energy, and even mass energy equivalents were all revealed or clarified because conservation could not be satisfied otherwise. The law also changes how motion is understood over time. Motion is no longer a fleeting event that must be constantly replenished. It is a temporary arrangement of energy. When that arrangement breaks down, energy continues in other forms. Motion is not consumed, it is reorganized. This makes the phrase, "motion never ends," more precise. Motion never ends in the sense that the energy responsible for motion never disappears. It continues to move, to vibrate, to propagate, even when it no longer produces the same large-scale effects. The law of conservation also eliminates the idea that the universe might one day simply run out of motion in a literal sense. Energy can become less available for doing work. It can spread out and reach states where large-scale motion is unlikely to reappear. But energy itself does not fade away with time. The universe does not forget it. This distinction becomes especially important when discussing large systems. Consider a closed container of gas. The molecules inside move constantly, colliding with each other and the walls. Over time, the system reaches equilibrium. Temperature becomes uniform. No large-scale flows remain. From the outside, the system looks static. But internally, motion continues relentlessly. Molecules do not stop. Energy has not vanished. It has simply reached a distribution where no net changes are visible at the macroscopic level. Conservation of energy guarantees that this internal activity persists. The same logic applies on cosmic scales. Stars burn fuel. They radiate energy into space. That energy does not disappear when it leaves the star. It travels outward, heating dust, driving chemical reactions, and eventually contributing to the background radiation of the universe. The star's motion and activity change form, but the energy remains part of the cosmic ledger. This also reframes the concept of efficiency. When a machine is described as inefficient, it does not mean it loses energy. It means it converts energy into forms that are not useful for the intended task. Heat generated by friction is still energy. It is simply energy that cannot easily be harnessed to produce directed motion. From this perspective, inefficiency is not a failure of conservation, it is a consequence of it. Because energy must go somewhere, and because many destinations are less useful than others, every real process produces side effects. The conservation of energy also undercuts the idea that motion needs to be continuously fed. Feeding motion is just one way of transferring energy. Once energy is in motion, it stays there unless it is transferred again. Time alone does nothing to it. This is why inertia and energy conservation fit together so naturally. Inertia describes the persistence of motion in the absence of forces. Energy conservation explains why that persistence does not drain anything. There is no cost to continuing motion. Costs arise only when motion changes. Together, these ideas form a picture of the universe that is fundamentally conservative rather than consumptive. Change happens not by burning through a supply, but by rearranging what already exists. Motion flows through systems rather than being spent. This picture also explains why apparent losses always show up as gains elsewhere. Heat warms surroundings, sound vibrates materials, light carries energy across space. No matter how diffuse or subtle the result, conservation demands that it be there. The law that changes everything does not tell us how energy will behave in detail. It tells us something more basic. It tells us what cannot happen. Energy cannot simply disappear. Motion cannot simply end without leaving a trace. Once this constraint is accepted, every discussion of motion changes character. Instead of asking where motion went, the question becomes where it moved to. Instead of asking why energy ran out, the question becomes how it was redistributed. And that shift in questioning opens the door to deeper understanding. It leads naturally to examining systems where motion seems to stop completely and asking what is really happening beneath the surface. It leads to the realization that even when nothing appears to be moving, energy is still in play, still flowing, still obeying the same unbreakable rule. From here, the conversation turns to a question that conservation alone does not answer. If energy is conserved and motion persists in some form, why does the universe so often settle into states where nothing noticeable seems to happen? Why does motion spread out instead of gathering itself back together? To understand that, we have to look more closely at what happens after energy is conserved, not in quantity, but in quality, and why some forms of motion are easier to recognize, while others quietly fill the universe without drawing attention to themselves. When something stops moving, it feels final. A wheel slows, settles, and becomes still. A swinging object comes to rest. A machine powers down. From the outside, the story seems complete. Motion happened, and now it has ended. But this sense of completion is a feature of human perception, not a feature of the universe. What actually happens when motion appears to stop is far more subtle, and once you look closely enough, the idea of complete stillness starts to dissolve. The first thing to let go of is the assumption that stopping is a single event. It is not a moment where motion switches off. It is a process where one pattern of motion breaks apart into many others. What we experience as stopping is the loss of coordination, not the disappearance of movement itself. Consider something as familiar as a rolling ball. As it moves across the floor, the motion is obvious. The path is clear. The speed can be judged. When it slows and finally comes to rest, the motion seems to be gone. But at the instant the ball appears still, its atoms are vibrating. The floor beneath it is vibrating. The air around it is in constant motion. Energy has flowed out of the organized rolling motion and into disorganized microscopic motion, but it has not ceased to move. The reason this feels like stopping is that human perception is tuned to large-scale patterns. We notice motion when many particles move together in a coherent way. We stop noticing motion when that coherence is lost. The transition from visible movement to thermal motion crosses a threshold where our senses are no longer useful. This threshold is arbitrary. It is defined by biology, not physics. If we had senses capable of tracking molecular motion directly, the world would never look still. Every surface would shimmer. Every object would buzz with activity. Silence and stillness would not exist in the way we understand them. This is not a philosophical exaggeration. It is a direct consequence of how matter behaves. At any temperature above absolute zero, particles move. They collide, vibrate, and exchange energy continuously. Absolute zero, the hypothetical state where all motion ceases, turns out to be unattainable. As systems approach it, removing the remaining energy becomes increasingly difficult. Motion resists extinction even under extreme conditions. This resistance is not stubbornness, it is structure. Motion persists because energy is conserved, and because there are always degrees of freedom available for it to occupy. When one pathway closes, another opens. The idea that nothing ever truly stops becomes even clearer when you examine what at rest actually means. Rest is not an absolute condition. It is always defined relative to something else. An object resting on a table is at rest relative to the table, but the table is moving with the Earth. The Earth is orbiting the Sun is orbiting the centre of the galaxy, and the galaxy itself is moving relative to other galaxies. Motion never disappears, it layers. This relativity of motion undermines the idea of a final resting state. There is no universal frame where everything stops. There are only relationships between motions at different scales. Even within a single frame of reference, rest often conceals activity. A parked car is not inert. Its engine components are cooling. Its tyres are deforming under weight. Its metal expands and contracts with temperature changes. Air flows around it. Electrons move through its circuits. Chemical reactions continue in its battery. The car appears still because its most obvious motion has ended, not because motion itself has. The same is true for systems we think of as stable or dead. A rock on the ground is not motionless, its atoms vibrate. Stress fields distribute weight. Radiation passes through it. It exchanges energy with its surroundings constantly. Over long timescales, it weathers, erodes, and changes shape. What looks like permanence is simply change happening slowly. Even silence is not an absence of motion. Sound fades because its organized vibrations spread out and become part of thermal motion in the air and surrounding materials. The room becomes quieter to us, but microscopically it becomes more active. This perspective also clarifies why motion appears to stop more completely in some cases than others. A sliding object on rough ground stops quickly because energy is transferred efficiently into heat. A spinning object on low-friction bearings stops more slowly because fewer pathways exist for energy transfer. In both cases, motion does not end. It changes form at different rates. The concept of stopping also breaks down when you look at systems in equilibrium. A glass of water left undisturbed will eventually appear completely still. No currents, no ripples. But inside that glass, molecules are moving constantly. They collide billions of times per second. Temperature represents the average kinetic energy of that motion. Equilibrium does not mean inactivity. It means balance. In equilibrium, energy flows are symmetrical. Motion continues, but no net change occurs at the macroscopic level. The system looks static because the motions cancel out statistically. This is one of the most important ways the universe hides motion from us. The same principle applies to larger systems. The atmosphere appears calm on a still day, but it is full of molecular motion. The ocean surface may look smooth, but currents flow beneath. A star may look steady, but its interior is a storm of nuclear reactions and energy transport. From this point of view, the universe is never idle. It never pauses. It never reaches a state where nothing happens. What it reaches, instead, are states where change becomes subtle, distributed, and hard to reverse. This is why the idea of motion ending is so closely tied to human timescales. On short timescales, motion transforms rapidly into heat and noise. On long timescales, even heat spreads and equilibrates. But at no timescale does motion truly vanish. Even in cases where motion seems to disappear into the environment completely, it has not been destroyed. It has joined a much larger system. Energy from a falling object becomes part of the thermal energy of the Earth. Energy from a star becomes part of the background radiation of the universe. The motion continues, but it is no longer localized. This leads to an important distinction between local stopping and global persistence. Locally, motion can end. A wheel can stop turning. A pendulum can come to rest. A person can stop walking. Globally, motion continues. Energy moves elsewhere. The system as a whole remains active. This distinction helps resolve a common confusion. When people hear that motion never ends, they imagine objects that never slow down, machines that run forever, or perpetual visible activity. That is not what the claim means. It means that the energy associated with motion never disappears. It means that every apparent ending is a handoff. The universe does not have a mechanism for erasing energy. It only has mechanisms for redistributing it. Motion can become harder to recognize, harder to use, harder to reverse, but it does not cease to exist. This is also why attempts to define a true endpoint for motion always run into problems. What would it mean for motion to stop absolutely? It would require a state where no particle moves, no field fluctuates, no energy transfers occur. Such a state is not just unreachable in practice, it is incompatible with the structure of physical law as we understand it. Even the vacuum, often imagined as empty and inactive, is not still. Fields fluctuate. Particles appear and disappear. Energy exists in forms that do not resemble motion in the everyday sense, but are nonetheless dynamic. This realization has deep implications for how we think about endings. Systems do not simply shut down, they transition. Motion does not vanish, it diffuses. Energy does not die, it disperses. Understanding this does not make motion eternal in a comforting or dramatic way. It makes it persistent in a technical sense. Motion continues because there is no rule that allows it to be destroyed. There is no drain where it can disappear. What changes over time is not whether motion exists, but how accessible it is. Early in a process, motion may be concentrated and useful. Later, it may be spread thin and inert from a practical point of view. But inert is not the same as non-existent. This distinction becomes especially important when thinking about the long-term behavior of systems. A machine wears out because its energy flows become inefficient, not because energy disappears. A living organism dies because it can no longer maintain the structures that channel energy into organized motion, not because energy leaves the universe. From the universe's perspective, nothing stops. From our perspective, things end all the time. The difference lies in scale and organization. As we continue, this understanding forces us to confront a deeper question. If motion never truly stops, and energy is always conserved, why does motion tend to spread out rather than reassemble itself? Why does the universe prefer disorganized motion over organized motion? Answering that question requires looking not just at energy, but at how it flows through systems over time, and why certain directions of change are overwhelmingly more likely than others. That path leads directly into the idea that motion has a direction, not because energy runs out, but because the ways energy can be arranged are not all equally probable. When motion is followed down to its smallest recognizable scales, it doesn't disappear, it multiplies. What looks like stillness at the human level becomes a dense, restless activity when viewed atom by atom. Understanding energy at the atomic scale is one of the clearest ways to see why motion never truly stops, because at that level, motion is not an occasional event, it is the default condition. Atoms are often pictured as tiny solid objects, like miniature billiard balls packed together. That image is useful for some purposes, but it hides more than it reveals. An atom is not a static thing. It is a system, a structure held together by forces and defined by motion. Electrons do not sit quietly in place. They occupy regions of probability, constantly interacting with electric fields. Atomic nuclei are not rigid cores. They vibrate, respond to forces, and participate in interactions that never truly shut off. In a solid object, atoms are arranged in a regular pattern, which gives the material its shape and rigidity. But that regularity does not imply stillness. Each atom vibrates around an equilibrium position. The higher the temperature, the more vigorous the vibration. Even at temperatures far below what feels cold to us, atomic motion persists. What we experience as warmth or cold is simply our sensory system, responding to differences in this microscopic activity. This is one of the first places where everyday intuition breaks down completely. A block of metal resting on a table feels solid and unmoving, but inside that block, atoms are oscillating thousands of billions of times per second. Bonds stretch and compress. Energy flows between neighbouring atoms through these vibrations. The structure holds because the forces are balanced, not because motion has stopped. At the atomic scale, energy is inseparable from motion. There is no meaningful way to talk about an atom having energy without that energy being expressed through some kind of movement, vibration, or field interaction. Even energy stored in bonds is not frozen. Chemical bonds are dynamic relationships between electrons and nuclei. They involve constant motion and exchange. This realization reshapes what stored energy means. When energy is stored in an atomic or molecular structure, it is not sitting idle, waiting passively. It is actively shaping how particles move and interact. A chemical bond represents a lower energy configuration compared to separated atoms, but that lower energy state is still full of motion. It is simply motion arranged in a stable pattern. Thermal energy provides the most direct link between atomic motion and everyday experience. Temperature is a measure of the average kinetic energy of particles. When an object heats up, its atoms move more vigorously. When it cools down, their motion slows, but slowing is not stopping. As temperature approaches absolute zero, atomic motion decreases, but it never reaches zero in any achievable system. This persistence is not a technical loophole. It is a consequence of the rules that govern matter. At very low temperatures, quantum effects become important. Particles retain motion even in their lowest energy states. This so-called zero-point motion means that even in the coldest possible conditions, particles are not completely still. Motion is built into the structure of matter itself. The atomic scale also reveals why friction and heat are so effective at hiding motion. When organized motion at the macroscopic level is transferred into atomic motion, it does not vanish. It becomes distributed across an enormous number of particles. Each particle gains a tiny amount of energy. The total energy is conserved, but no single particle moves in a way that stands out. This distribution makes motion hard to reverse. To reassemble atomic scale motion into macroscopic motion, countless particles would have to coordinate their movements. They would need to align phases, directions, and timings in just the right way. The laws of physics do not forbid this, but the odds are so small that it effectively never happens on its own. Atomic motion also explains why materials behave differently under stress. When you bend a piece of metal, you're not simply moving a rigid object. You're rearranging atomic positions. Bonds stretch, some break and reform. Energy flows into the atomic lattice. When the metal returns to its original shape, some of that energy is recovered as motion. When it does not, the energy has been redistributed into permanent rearrangements and heat. This microscopic view dissolves the idea that motion is something added from the outside. Motion is already there. External forces do not create motion from nothing. They redirect existing motion, concentrate it, or alter its organization. Even electrical energy becomes clearer at this scale. Electric current is not a stream of electrons racing through a wire at high speed in the way people often imagine. It is a slow drift of charge carriers combined with rapid electromagnetic interactions. The energy transfer happens through fields and interactions that propagate at near light speed, not through the bulk motion of particles alone. Again, motion is present, but not always in the form intuition expects. Light itself, when examined at atomic scales, reinforces the same theme. Light carries energy through oscillating electric and magnetic fields. When light is absorbed by an atom, that energy changes the atom's internal motion. Electrons shift to different states. Vibrations increase. Eventually, the energy spreads into thermal motion. Light disappears from view, but its energy lives on as atomic motion. What becomes unavoidable at this scale is the realization that stillness is an illusion created by averaging. We average over space. We average over time. We average over enormous numbers of particles. The result is a calm picture that hides intense underlying activity. This averaging is useful. Without it, the world would be incomprehensible. But it comes at a cost. It convinces us that motion can end completely. Atomic physics shows that this is never the case. Even in systems that appear perfectly stable, energy is flowing. Consider a crystal at thermal equilibrium. Its macroscopic properties are constant. Its shape does not change. Its temperature remains steady. But energy is constantly exchanged between atoms. Vibrations propagate as waves through the lattice. These waves interact, scatter, and redistribute energy continuously. The system is dynamic even though nothing changes in a way we can see. This dynamic stability is one of the most important features of matter. It allows structures to persist without being rigidly frozen. It allows materials to respond to stress, conduct heat, and interact with their environment. Motion is what gives matter its flexibility and resilience. The atomic scale also clarifies why motion can never be perfectly localized. When energy enters a system at one point, it spreads. Atomic interactions carry energy away from the source. Heat conduction is the macroscopic result of this microscopic spreading. Over time, energy disperses until it is shared as evenly as possible. This spreading is not driven by a desire for uniformity. It is driven by probability. There are vastly more atomic configurations that correspond to energy being spread out than concentrated. Systems evolve toward those configurations because they are overwhelmingly more likely. At the atomic level, this tendency is not mysterious. Particles collide. They exchange energy. Over many interactions, the energy distribution smooths out. The process does not require guidance or intention. It emerges from countless small interactions governed by simple rules. This perspective also helps explain why energy conservation does not contradict the everyday experience of cooling and slowing. When a hot object cools, energy leaves it and enters the surrounding environment. The total energy is conserved. The object's atomic motion slows. The environment's atomic motion increases. Motion has not stopped. It has spread. From the atomic viewpoint, the universe is a continuous sea of motion. There are no isolated still points. There are only regions where motion is more or less organized, more or less visible, more or less useful for particular purposes. Even what we call empty space is not truly empty at this scale. Fields fluctuate. Particles appear and vanish briefly. Energy exists in forms that do not resemble motion in the classical sense, but are nonetheless dynamic. The idea of absolute stillness has no foothold. Once motion is understood as something embedded in the structure of matter itself, the phrase, "why motion never ends," becomes less of a puzzle and more of an observation. Motion does not need to be sustained because it is already there. It does not need to be created because it cannot be removed. What changes is not whether motion exists, but how it is arranged. Organized motion becomes disorganized. Concentrated energy becomes diffuse. Visible movement becomes thermal vibration. The scale shifts, but the activity remains. This atomic perspective also sets the stage for understanding motion on larger scales in a new way. The The same principles that govern vibrating atoms also govern flowing fluids, orbiting planets, and expanding galaxies. The details differ, but the logic is consistent. By grounding motion in atomic behavior, it becomes clear that stopping is always partial and local. Motion ends for a particular object in a particular way, but it continues elsewhere, carried by particles, fields, and interactions that never shut down. As the lens widens again from atoms to larger systems, this insight remains crucial. It reminds us that whenever motion appears to end, we are not witnessing a failure of energy or a violation of physical law. We are witnessing a redistribution so thorough that motion has crossed a boundary of perception, and with that understanding in place, the next step is to move outward, away from atoms and toward the vast systems where motion operates on scales that dwarf human experience, to see how the same persistence of energy plays out among planets, stars, and the structure of the universe itself. When attention shifts from atoms to the largest structures in existence, motion does not fade into insignificance, it becomes unavoidable. On the scale of planets, stars, galaxies, and beyond, motion is not something that occasionally happens. It is the dominant condition. Nothing large in the universe is truly still, and the farther outward you look, the clearer that becomes. At human scales, motion is easy to mistake for something local and temporary. Objects move through rooms, vehicles travel along roads, people walk, stop, sit, and sleep. The background feels stable, the ground beneath your feet feels fixed, the sky feels like a backdrop. But that feeling is the result of perspective, not physics. The Earth itself is in constant motion, and every large-scale motion you experience is layered on top of motions that are vastly larger and older than anything in daily life. The ground beneath you is rotating with the Earth once every day. At the equator, this motion is faster than a commercial airplane. You do not feel it because everything around you is moving at the same rate. The atmosphere, the oceans, the ground, your body, all share this motion. From your local frame of reference, nothing appears to be happening, but the motion is there, constant and immense. At the same time, the Earth is orbiting the Sun. This motion is even faster, tens of kilometers per second. Again, you do not feel it because it is smooth and shared. The Sun, in turn, is orbiting the center of the Milky Way galaxy, carrying the entire solar system along with it. That motion takes hundreds of millions of years to complete a single loop, but it never stops. The galaxy itself moves relative to other galaxies, participating in larger flows shaped by gravity on cosmic scales. These layered motions reveal something important. Stillness is always relative. What looks stationary from one viewpoint is moving rapidly from another. There is no universal reference point where everything can be said to be at rest. Motion never ends because there is no place for it to end against. On these scales, inertia shows its full power. Once large objects are set in motion, they tend to stay that way for extraordinarily long periods. Planets do not need engines to keep orbiting stars. Stars do not need fuel to keep orbiting galactic centers. Their motion persists because space offers very little resistance. The universe is not empty, but it is sparse enough that motion is rarely interrupted. Gravity plays a central role in shaping motion at these scales, but it does not behave as an agent that constantly pushes objects along. Gravity bends paths, it curves trajectories, it causes objects to accelerate toward one another, but once motion is established, gravity guides it rather than sustaining it. Orbital motion is not a struggle against collapse. It is a balance between inertia and gravitational attraction. This balance produces some of the most stable motions in the universe. Planetary orbits can persist for billions of years with only small changes. Stars within galaxies follow paths that remain coherent over cosmic timescales. Entire galaxies move through space in patterns set shortly after the universe's earliest moments. These motions do not fade because there is little to drain their energy. Interstellar space is thin. Intergalactic space is even thinner. There are particles, radiation, and fields present, but not enough to act as effective friction on large objects. Motion, once established, continues almost indefinitely. This persistence makes large-scale motion feel different from everyday motion. There is no obvious slowing, no visible decay. Motion becomes part of the structure of the system, rather than a temporary event. A galaxy is not something that moves through space and might one day stop. Its motion is part of what it is. The same is true for the expansion of the universe itself. On the largest scale of all, space is stretching. Galaxies are moving away from one another not because they are flying through space like debris from an explosion, but because the space between them is expanding. This motion is not localized. It is built into the geometry of the universe. Once again, motion does not need to be maintained. The expansion proceeds according to the energy content and structure of space-time itself. There is no external environment for it to rub against, no background into which its energy could be drained. It does not slow because it is not pushing against anything in the way everyday intuition expects. This cosmic motion reinforces the idea that motion is not an activity that consumes itself. It is a state that evolves according to constraints. When conditions allow motion to persist without interference, it does so. Even on these scales, however, motion does not remain perfectly organized forever. Interactions still occur. Galaxies collide. Stars exchange energy. Gas clouds collapse. Energy flows and redistributes. Motion changes form, but it does not disappear. When galaxies collide, their stars mostly pass by one another without direct contact. The motion of billions of stars continues, altered but not destroyed. Gas clouds compress, heating up and forming new stars. Gravitational energy converts into thermal energy and radiation. Motion transforms, but the total energy remains accounted for. These events show that even violent cosmic processes follow the same rules as a sliding block or a spinning wheel. The scale changes, the drama increases, but the logic remains consistent. Energy shifts from organized orbital motion into heat, radiation, and new forms of structure. This is why the universe does not settle into stillness even over billions of years. Energy continues to flow between forms. Motion reorganizes itself rather than ending. Structures form, evolve, and dissolve, but the underlying activity never stops. One reason this is difficult to grasp is that cosmic timescales dwarf human experience. A motion that appears eternal to us may be fleeting on cosmic scales. A star's lifetime feels unimaginably long, yet stars are born and die continuously. Galaxies change shape. Clusters evolve. Motion persists, but the patterns it takes shift slowly. From a distance, these slow changes can look like stability, but stability is not inactivity. It is motion arranged in a long-lived configuration. The larger scales also reveal something else about motion. It does not require complexity to persist. Even simple systems can maintain motion for extraordinary lengths of time if interactions are limited. A lone particle drifting through empty space will continue forever unless it encounters something else. Its motion has no built-in expiration date. This stands in stark contrast to how motion feels at human scales, where interactions are unavoidable and energy dissipates quickly into heat. The difference is not in the nature of motion, but in the density of interactions. On Earth, motion is constantly being redistributed. In space, it is not. This contrast helps explain why motion appears fragile in daily life and robust in the cosmos. We live in one of the most interaction-heavy environments imaginable. Matter is dense, temperatures are moderate, surfaces are rough. Motion is constantly being broken down and spread out. The universe at large is far quieter in that sense, even though it is never still. Another important feature of large-scale motion is that it is often collective. Stars in a galaxy move together in patterns set by gravity. Galaxies and clusters move in coordinated ways. These collective motions are not imposed externally. They emerge from mutual interactions over long periods. Once established, they become self-maintaining in the sense that no additional input is required to keep them going. Energy remains bound up in motion that spans vast distances and times. This collective behaviour also makes large-scale motion harder to disrupt. To significantly alter the motion of a galaxy requires enormous energy. Small perturbations are absorbed and redistributed. The system adapts rather than stopping. Here again, motion resists endings. It flows around obstacles. It reorganizes. It finds new expressions. Even when motion seems to slow on cosmic scales, it does so through redistribution, not disappearance. When a star exhausts its nuclear fuel, its internal motions change. It may collapse, explode, or settle into a compact object. Energy is released as radiation. Matter is ejected. Motion continues, transformed. The death of stars does not reduce the universe's motion. It reshapes it. Supernovae drive shock waves. Radiation streams outward. New structures form. Energy spreads, but it does not vanish. On the larger scales, this process becomes a story of continual rearrangement rather than decay. Structures form where energy becomes concentrated. They dissolve as energy spreads. Motion never ends. It migrates. This perspective also challenges the idea that the universe might one day become completely motionless. Even in scenarios where large-scale structures fade and energy becomes more evenly distributed, motion persists at microscopic scales. Particles continue to move. Fields continue to fluctuate. Radiation continues to propagate. The universe may change character over time, but it does not shut down. Seeing motion at the larger scales makes it clear that the everyday experience of stopping is a local phenomenon. It is a consequence of living in a dense, interactive environment. It is not a statement about how motion behaves in general. Motion never truly stops, because there is nowhere for it to go where it could be erased. It can only change form and scale. As the focus moves from galaxies and cosmic expansion back toward the flow of time and the direction of change, this realization becomes essential. If motion persists everywhere, why does it seem to flow in a particular direction? Why does energy spread out rather than spontaneously gathering itself back into organized forms? The answer lies not in the conservation of energy alone, but in how motion interacts with probability and structure over time, shaping the arrow of change that governs everything from cooling cups of coffee to the long-term evolution of the universe itself. Motion persists, but it does not remain arranged in the same way. This is where the idea of entropy enters, not as a mysterious force pushing the universe toward decay, but as a way of describing how motion and energy naturally reorganize themselves over time. Entropy does not tell energy where to go. It tells us which arrangements of energy are overwhelmingly more likely than others, and once that distinction is understood, the apparent direction of change in the universe stops looking like a countdown and starts looking like a consequence of probability. At its core, entropy is a measure of how many microscopic configurations correspond to a given macroscopic state. That sounds abstract, but it maps directly onto physical reality. Any large system, whether it is a gas in a box, a warm object in a cool room, or a galaxy full of stars, can be arranged internally in many different ways. Some arrangements are highly specific and organized. Others are loose, spread out, and disordered. The crucial point is that there are vastly more disordered arrangements than ordered ones. Because systems move according to physical laws that allow many microscopic rearrangements, they tend to evolve towards states that can be realized in more ways. This is not a preference or a goal. It is a statistical fact. When energy is free to move and redistribute, it will almost always spread out rather than concentrate itself into a precise pattern. This is why entropy is often misunderstood as a force. It is not pushing anything. Nothing is being driven downhill. Instead, Systems wander through the space of possible configurations, and because there are far more high-entropy configurations available, they almost inevitably end up there. To see how this connects to motion, consider what happens when organized motion turns into heat. A rolling object slows down. Its motion energy becomes thermal energy. At the microscopic level, this means that instead of many particles moving together in one direction, energy is shared among countless particles moving independently. The total energy is the same, but the number of possible arrangements has exploded. There are very few ways for trillions of particles to move in a coordinated way that produces a rolling object. There are astronomically many ways for those same particles to move randomly while conserving the same total energy. Once energy enters that larger space of possibilities, it is extremely unlikely to wander back into the tiny subset that corresponds to visible, organized motion. This is why entropy gives change a direction. Not because the laws of motion are asymmetric in time, but because probability is. The fundamental equations that govern particle interactions work just as well forward as backward. Nothing in the basic rules forbids a shattered glass from reassembling itself, or a cooled object from spontaneously heating up by drawing energy from its surroundings. But the number of microscopic configurations that would make those events happen is so small compared to all other possibilities that they effectively never occur. This distinction is subtle, but essential. Physics does not say that energy must spread out. It says that energy can spread out in many more ways than it can concentrate. Given enough time and freedom to interact, systems will almost always move toward the states that are easier to realize. Entropy is therefore not about loss, it is about accessibility. As entropy increases, energy becomes less accessible for producing coordinated motion. It is still there, it is still moving, but it is moving in ways that cancel out at large scales. This is why entropy fits so naturally into the story of motion never ending. Motion does not stop. It becomes less directed. It becomes harder to harness. It becomes distributed across more degrees of freedom. This also explains why entropy is tied so closely to irreversibility. A process is irreversible not because it breaks a rule, but because reversing it would require an implausible level of coordination. All of the tiny motions would have to line up just right, at just the right time, to recreate the original state. The laws of physics allow it. The statistics do not. Consider mixing cream into coffee. At first, the cream forms visible swirls. Motion is organized. Over time, the mixture becomes uniform. The motion continues at the microscopic level, but the large-scale patterns disappear. The entropy of the system increases because there are far more ways for the cream and coffee molecules to be evenly mixed than for them to be separated into distinct regions. Nothing has been lost. No energy has vanished. The system has simply moved into a state that is easier to realize and harder to undo. This same logic applies to every process where motion appears to fade. A pendulum comes to rest. A sound dies away. A hot object cools. In each case, energy spreads into more particles and more directions. Entropy increases. Motion persists, but its ability to organize itself into a visible pattern declines. Entropy also explains why time seems to have a direction. We remember the past and not the future, because memory formation itself is an entropy-increasing process. Creating a memory involves physical changes in the brain that leave traces. Those traces require energy to be spread and reorganized. The future has no traces yet. The past does. The direction we call forward in time is the direction in which entropy increases. That does not mean time is caused by entropy. It means our experience of time is shaped by the same statistical asymmetry that governs energy distribution. This connection becomes clearer when you imagine a universe with decreasing entropy. In such a universe, disordered states would spontaneously organize. Heat would flow from cold to hot. Broken objects would reassemble. Memory would run backward. Such a universe is not forbidden by physical law, but it is so improbable that it does not resemble anything we observe. Our universe started in a state of relatively low entropy. Energy was unevenly distributed. Structures could form, motion could organize itself into stars, planets, and living systems. As time progresses, entropy increases, energy spreads, structures become harder to maintain, motion becomes less concentrated. Importantly, increasing entropy does not mean that motion slows down overall. It means that motion becomes more evenly spread. The universe does not become static, it becomes uniform. Motion persists at every scale, but large-scale gradients flatten out. This is why entropy does not contradict the conservation of energy. Energy remains constant. Entropy measures how that energy is arranged. One can increase, while the other remains unchanged. This distinction helps resolve a common misunderstanding. When people hear about entropy increasing, they often imagine energy being used up or motion winding down. What is actually happening is that the universe is exploring more of its available configurations. Motion is not disappearing, it is becoming less structured. Even in the far future, if energy becomes evenly distributed across vast regions of space, motion will not stop. Particles will continue to move, radiation will continue to propagate, fields will continue to fluctuate. What will be lost is not motion but contrast. Contrast is what allows motion to do interesting things. Temperature differences drive heat flow. Pressure differences drive winds. Energy differences drive chemical reactions. As entropy increases, these differences shrink. Motion becomes quieter, not absent. This also explains why life and machines require constant energy input. They are local islands of low entropy. They maintain organized motion by exporting entropy to their surroundings. They do not violate the overall trend. They participate in it. Seen this way, entropy is not the enemy of motion. It is the reason motion takes the forms it does. It explains why motion flows from concentrated to dispersed, from organized to randomized, without ever being destroyed. Entropy does not say that motion must end. It says that motion changes its character over time in predictable ways. It tells us why motion that starts out obvious becomes subtle, and why recovering it becomes harder and harder. As the discussion moves forward, this understanding becomes critical when asking what the long-term future of motion looks like. If energy is conserved and entropy increases, what does that mean for the universe as a whole? Does motion simply fade into uniform background activity, or does it continue to find new ways to express itself? Answering that requires looking not just at entropy as a concept, but at how it interacts with structure, expansion, and the ongoing rearrangement of energy across the largest possible scales. Once entropy enters the discussion, it becomes tempting to tell a very specific kind of story about the universe. It is a story that sounds intuitive, almost unavoidable. Energy spreads out, motion becomes less organized, differences fade. Eventually, everything should slow down, flatten out, and settle into a quiet, featureless state. From this perspective, the universe is often described as running down, like a machine winding toward a final stop. Motion never truly ends in principle, but in practice it becomes so diffuse that nothing interesting can happen anymore. This story is not entirely wrong, but it is incomplete in a way that matters. It frames change as exhaustion rather than transformation. It emphasizes what disappears while ignoring what continues. And most importantly, it treats entropy as a destination rather than a process. To understand what is really happening, it helps to step back and ask a different question. When entropy increases, is the universe losing something, or is it rearranging itself into states that are easier to realize? The answer to that question changes how we interpret everything that follows. The idea of the universe running down comes from extending everyday experience to cosmic scales. Machines wear out, batteries drain, fires burn out, motion fades. These experiences are real, but they occur in systems that are small, open, and embedded in larger environments. A machine stops not because energy disappears, but because it can no longer channel energy into organized motion. The surrounding environment continues to absorb that energy. From the machine's point of view, the story ends. From the universe's point of view, it does not. When this logic is applied to the universe as a whole, problems appear. The universe does not sit inside a larger environment that can absorb its energy. There is no external sink. Everything that happens within the universe. Energy does not leave the system, it rearranges within it. This alone should make the phrase running down feel questionable. Running down implies depletion. It implies that something is being used up, but energy is conserved. Nothing is being consumed in a way that reduces the total. What entropy actually describes is not depletion, but redistribution. Energy moves from concentrated forms into more evenly spread ones. Gradients flatten, differences shrink, but motion itself continues. Particles still move, fields still fluctuate, radiation still propagates. The universe does not go quiet, it becomes more uniform. Uniformity is often mistaken for stillness. When large-scale differences disappear, the motions they once drove fade from view. Without temperature differences, there is no heat flow. Without pressure differences, there are no winds. Without energy gradients, there are no obvious sources of large-scale change. But the absence of large-scale change is not the absence of motion. This distinction matters because it shifts the question from will motion end to what forms of motion will remain. The universe does not approach a final stop. It approaches a state where motion is harder to organize into new structures. The classic image associated with this idea is the so-called heat death of the universe. In that scenario, energy becomes evenly distributed across space. No region is significantly hotter or colder than another. No work can be extracted because there are no gradients to exploit. From a practical standpoint, nothing interesting happens. But even in this scenario, motion does not end. Thermal motion persists. Particles continue to move. Radiation continues to travel. Quantum fluctuations continue to occur. What disappears is not motion itself, but the ability for motion to concentrate and reorganize into new macroscopic patterns. Calling this outcome a death reflects human priorities, not physical ones. From the universe's perspective, nothing has gone wrong. Energy is conserved. Motion continues. The system has simply moved into a configuration that is overwhelmingly likely given enough time. This reframing reveals something subtle. Entropy does not drive the universe towards stillness. It drives it towards states that are statistically dominant. Those states happen to look uneventful to creatures who depend on gradients to function. Life, machines, weather, and geology all rely on uneven energy distributions. They exist in a universe that has not yet smoothed itself out. As entropy increases, maintaining those uneven distributions becomes harder. That is why such systems are temporary. But their temporary nature does not imply that the universe itself is fading. Another way to see this is to focus on rearrangement rather than decline. When energy spreads, it does not vanish, it relocates. Motion shifts from one scale to another. Organized motion becomes disorganized motion. Concentrated energy becomes diffuse energy. The total activity does not diminish. Its structure changes. This is already familiar at smaller scales. A spinning wheel slows down. The motion energy becomes heat. The wheel stops turning, but the environment becomes slightly warmer. The system as a whole has not become less active. It has become more evenly active. Extend that logic outward, and the same pattern holds. Stars burn fuel and radiate energy. That energy spreads through space. The star's internal motion changes. New motion appears elsewhere. Over time, stars exhaust their nuclear fuel. Their structures change, but the energy they released continues to move through the universe. Galaxies evolve in similar ways. Gas clouds collapse, form stars, and disperse. Motion is redistributed. Structures appear and disappear. Over long time scales, the universe rearranges its energy landscape. At no point in this process does motion need to end. It only needs to change form. The phrase running down also suggests a monotonic decline, as if everything simply becomes less and less active over time. But the universe's history does not look like a smooth descent. It looks like a sequence of transitions. Early on, energy was extremely concentrated. Then it spread, forming particles, atoms, stars, and galaxies. New kinds of motion became possible at each stage. Complexity increased locally, even as entropy increased globally. This apparent contradiction is resolved once you recognize that entropy can increase overall while decreasing locally. Local decreases in entropy are paid for by larger increases elsewhere. Structure formation is not a rebellion against entropy. It is one of the ways entropy increases. When matter clumps under gravity, potential energy is converted into heat and radiation. The clump becomes more ordered, but the environment becomes more disordered. The total entropy goes up. Motion does not disappear. It shifts location and scale. This process continues today. Stars form, planets form, life emerges. None of these events violate the trend toward higher entropy. They are expressions of it. Seen this way, the universe is not winding down like a clock. It is exploring its available configurations. Early on, energy was unevenly distributed in ways that allowed dramatic changes. Later, energy becomes more evenly distributed and dramatic changes become rarer. But the underlying activity never ceases. This perspective also helps clarify why discussions of the universe's fate often feel emotionally loaded. A future with fewer stars and less structure feels bleak because it lacks the kinds of motion that matter to us. But physics does not privilege our interests. It does not define meaning in terms of habitability or complexity. It tracks energy and motion. From that point of view, a universe filled with low-level thermal motion and radiation is not dead. It is active in a quieter way. Another misconception embedded in the running down narrative is the idea that entropy is something new being added to the universe, like a contaminant that accumulates. In reality, entropy is a description of how energy is arranged. It does not build up as a substance. It increases because systems move toward more probable configurations. There is no reservoir of entropy filling up. There is only energy rearranging itself into patterns that are easier to realize. This distinction matters because it avoids treating entropy as an external threat to motion. Motion does not lose a battle against entropy. Motion expresses itself through entropy. When motion is highly organized, entropy is low. When motion is disorganized, entropy is high. Both states involve motion. They differ in how coordinated that motion is. The question, then, is not whether the universe will stop moving, but whether it will continue to produce new organized motions. That depends on the availability of gradients and the structure of space-time itself. Cosmic expansion complicates this picture further. As space expands, energy densities decrease, radiation stretches, matter spreads out. This expansion can both increase entropy and create new conditions for motion. It changes how energy interacts over large distances. In an expanding universe, energy does not simply settle into a final static arrangement. The stage itself changes. Space grows, horizons form, regions become causally disconnected. Motion continues within those regions even as they drift apart. This means that even a highly entropic universe is not frozen in a single configuration. It continues to evolve. The patterns change. The scale of interaction shifts. From this vantage point, the future of the universe is not a single endpoint but a regime. A regime where motion is mostly microscopic and diffuse, where large-scale structures are rare or absent, where change happens slowly and quietly. Calling that state running down captures only half the story. It captures the loss of familiar structures. It misses the persistence of motion itself. A better description is rearrangement. Energy rearranges, motion rearranges. The universe explores its possibilities until it occupies the ones that dominate statistically. This reframing also removes the implication that motion once had more meaning and now has less. Meaning is a human assignment. Physics concerns itself with consistency. As long as energy is conserved and interactions occur, motion continues. Understanding this prepares the ground for a more nuanced view of endings. Endings are local. Structures end, patterns end, processes end. Motion does not. The universe is not a machine that is slowly grinding to a halt. It is a system that is gradually redistributing its energy into configurations that are easier to maintain. The activity does not vanish. It becomes quieter, more uniform, and less capable of producing the kinds of change we recognize easily. From here, the natural question is not whether motion ends, but whether anything can interrupt this trend. Are there processes that can reverse or reshape the flow of energy in ways that sustain structure longer than entropy alone would suggest? Are there pockets of the universe where motion remains organized far longer than intuition would predict? Answering that requires turning attention to one of the most surprising manifestations of energy flow, life itself, a phenomenon that exists entirely because motion never ends, and because energy, even as it spreads, can still be temporarily organized into patterns that resist uniformity. Life is often described as a thing, a category, a special kind of matter that behaves differently from everything else. But when you strip away the language and the emotion attached to it, life is not a substance at all. It is a process. More specifically, it is a pattern of organized motion that persists by continuously redirecting energy. Life exists not in spite of the tendency toward disorder, but because of it. Every living system is built on motion, not metaphorical motion, not poetic motion, but physical motion at every scale. Molecules move through cells, ions flow across membranes, proteins fold, unfold, and change shape. Chemical reactions proceed in tightly regulated sequences. Fluids circulate, signals propagate. Nothing inside a living organism is still, even when the organism appears to be at rest. This constant activity is not incidental, it is essential. The moment the motion stops in a coordinated way, life ends. Not because energy disappears, but because the organization that channels that energy collapses. From a physical perspective, a living organism is an open system. It takes in energy from its environment, uses that energy to maintain internal order, and releases energy back into the environment in a more disorganized form. This flow is continuous. The moment it stops, entropy catches up locally, and the organized structure breaks down. This is why life cannot exist without a constant energy supply. Food, sunlight, chemical gradients, all of these are sources of energy that life taps into. But life does not use energy to create motion from nothing. It uses energy to maintain specific patterns of motion against the background tendency for energy to spread out. A living cell, for example, is not a static container full of chemicals. It is a dynamic network. Molecules are constantly being built and broken down. Energy-rich compounds are synthesized and consumed. Waste products are expelled. Membranes maintain electrical and chemical gradients by actively moving ions against their natural tendency to diffuse. All of this requires motion, and all of it requires energy to be continuously redirected. What makes this remarkable is not that life violates entropy, but that it works with it. Every action a living system takes increases the total entropy of the universe. The organism stays organized by exporting disorder to its surroundings. Heat is released, waste products diffuse, energy spreads out. Locally, order is preserved. Globally, entropy increases. This balance is delicate. It depends on the environment providing usable energy in a consistent way. On Earth, that energy ultimately comes from the sun. Sunlight drives photosynthesis. Photosynthesis stores energy in chemical bonds. That stored energy flows through ecosystems, powering motion at every level, from molecular reactions to muscle contractions. At no point in this chain does energy stop moving. It changes form repeatedly, but it never disappears. The motion that begins as nuclear reactions in the sun becomes electromagnetic radiation, then chemical energy, then mechanical motion, then heat. Life is one of the many pathways through which this energy flows. Seen this way, life is not separate from the rest of physics. It is a particular way of organizing energy flow. It is a set of structures that persist because they are good at channeling energy from concentrated sources into dispersed sinks. This perspective also clarifies why life is temporary. Organisms age, break down and die because the structures that organize motion degrade over time. Maintaining order requires constant repair. Errors accumulate. Energy pathways become less efficient. Eventually, the system can no longer sustain the level of organization required. Death, in physical terms, is not the loss of energy. It is the loss of coordination. The energy that once flowed through the organism continues to exist. It disperses into the environment as heat and chemical matter. Motion does not end. The pattern ends. This distinction matters because it removes any implication that life is an exception to the rules governing motion. Life does not escape entropy. It rides it. It creates local order precisely because global disorder increases. Even the complexity of living systems does not contradict this. Complexity emerges because energy gradients exist. Where energy flows, structures can form that redirect that flow. Over time, some of those structures become very good at persisting. Natural selection favours configurations that maintain themselves longer by managing energy more effectively. This does not require intention or foresight. It requires only variation and persistence. Structures that collapse quickly disappear. Structures that channel energy efficiently remain. Over time, this leads to increasingly elaborate ways of organising motion. At every stage, motion remains central. Genetic information is copied through molecular motion. Neural signals propagate through electrical and chemical changes. Muscles contract through coordinated protein movements. Thought itself is a pattern of electrical and chemical activity in the brain. Life does not sit on top of motion. It is motion. This also explains why life feels active even when nothing obvious is happening. A sleeping organism is still metabolizing. A plant standing still is still transporting water, synthesizing molecules, and responding to its environment. Apparent stillness masks intense internal activity. The same principle applies at larger biological scales. Ecosystems are flows of energy and matter. Nutrients cycle. Populations grow and decline. Motion occurs not just in individual organisms, but in the movement of materials through food webs and environments. Even evolution itself can be understood in terms of motion. Genetic information moves through populations over time. Mutations introduce variation. Selection filters outcomes. Energy availability shapes which structures persist. Motion unfolds across generations rather than seconds. Life, then, is not a break in the story of energy and motion. It is a chapter that becomes possible because motion never ends. Without the persistent flow of energy, there could be no metabolism, no repair, no reproduction, no adaptation. This perspective also removes the temptation to treat life as fragile in a cosmic sense. Individual organisms are fragile, species are temporary, but the processes that give rise to life are robust wherever conditions allow sustained energy flow and complex chemistry. Motion does not need special permission to organize itself. Given gradients and time, it will explore possibilities. From this point of view, life is not fighting against the universe's tendency toward equilibrium. It is one of the ways the universe moves toward equilibrium. By accelerating the redistribution of energy, life increases entropy faster than many non-living processes would on their own. This is why biological activity often transforms environments dramatically. Oxygen accumulates, atmospheres change, landscapes are reshaped. These changes reflect altered energy flows. Life reorganizes motion on planetary scales. And yet, even this planetary impact does not halt the underlying trend. Energy continues to spread. Structures rise and fall. Motion persists. Understanding life as organized motion also reframes questions about purpose and meaning. Physics does not assign goals. It describes constraints. Life does not exist because the universe wants it to. It exists because energy flows can support it for a time. This does not diminish life. It situates it. It makes life part of a continuous story rather than an exception. Seen through this lens, the persistence of motion is what makes life possible in the first place. If energy could be destroyed, if motion could truly end, there would be no stable flows to build upon. No gradients, no cycles, no continuity. Life depends on the fact that energy remains available, even as it spreads. It depends on the fact that motion can be redirected, stored, released, and transformed without vanishing. As long as energy continues to flow, even quietly, the possibility of organized motion remains. It may not take the form of life as we know it forever, but the underlying principle does not change, and that realization leads naturally to a more personal scale of the same idea. If life as a whole is organized motion, then individual living beings are temporary patterns within that flow, patterns that exist for a while, channel energy, and then dissolve back into the larger motion of the universe without ever bringing that motion to an end. From a distance, it's easy to talk about energy, motion, and entropy as abstract ideas that apply to stars, atoms, and vast systems beyond everyday life. But those ideas do not stop at the edge of the cosmos or the boundary of biology. They pass directly through you. Not metaphorically, not symbolically, but physically. Right now, as you listen, energy is moving through you in carefully structured ways, sustaining a pattern that will not last forever, but does not vanish when it ends. You're not a container of energy in the way a battery is a container. You're a flow. Matter enters you. Matter leaves you. Energy enters you. Energy leaves you. What remains recognizable as you is not the material itself, but the organization of motion that persists for a while. Every moment of your existence depends on motion continuing. Your heart contracts and relaxes. Electrical signals travel along nerves. Molecules collide and react. Ions move across membranes. Proteins shift shape. Fluids circulate. Heat dissipates. None of this stops while you are alive, even briefly. There is no pause state. If these motions cease in a coordinated way, life ends immediately. This is not poetic language. It is a literal description. Life does not reside in stillness. It resides in controlled instability, in motion that is tightly regulated but never absent. Even when you feel still, you are not. Sitting quietly, lying down, sleeping, your internal activity continues relentlessly. Breathing slows, but it does not stop. Metabolism shifts, but it does not halt. Repair processes continue. Waste products are transported away. Energy keeps flowing. The sense of being a stable object comes from continuity, not immobility. The pattern persists even though the components are constantly changing. The atoms in your body today are not the same ones you had years ago. Many are not even the same ones you had months ago. What persists is not the matter, but the arrangement of motion that matter participates in. This is one of the most counterintuitive implications of energy conservation and entropy when applied to human beings. You do not persist by holding on to energy, you persist by passing it through. Food enters your body carrying chemical energy. That energy is transformed into motion, heat, electrical activity, and chemical work. Some of it becomes part of your structure temporarily. Some of it is used immediately. All of it eventually leaves. The system stays intact only because energy keeps moving. If energy stopped flowing through you, even for a short time, the organized motion that defines you would collapse. Not because energy disappeared from the universe, but because the structure that directed it could no longer be maintained. This makes you a temporary pattern in a very literal sense. Temporary does not mean trivial or insignificant. It means bounded in time. Your existence has a beginning, a duration, and an end, but at no point does energy itself begin or end. It only changes the way it moves. When your body eventually stops functioning as a living system, the energy that once flowed through it does not vanish. Heat dissipates into the surroundings. Chemical energy remains in tissues and is released through decay and consumption by other organisms. Atoms disperse. Motion continues in new forms. Nothing that makes you physically real is destroyed. What ends is the specific organization that allowed energy to flow in a way we recognize as you. This perspective can feel unsettling at first, because it challenges the idea of identity as something fixed and self-contained. But it also reveals a deeper continuity. You're not separate from the energy flows that shape the universe, you're one expression of them. From this point of view, birth is not the creation of energy. It is the emergence of a new pathway for energy flow. Death is not the destruction of energy. It is the closure of that pathway and the opening of others. This is not a statement about meaning or value. Physics does not assign those. It is a statement about structure and process. What we call a person is a complex temporary solution to the problem of how energy can move through matter under specific conditions. Those conditions include temperature ranges, chemical availability, gravity, radiation, and time. Change any of them enough, and the pattern cannot persist. That is why life is local and finite. It exists where motion can be organized in just the right way. Understanding yourself as a pattern of energy also clarifies why effort feels the way it does. When you exert yourself, you're not spending energy in a way that reduces the universe's total. You're redirecting energy through your body more rapidly. Heat increases, waste products accumulate, motion intensifies. Fatigue occurs not because energy disappears, but because the pathways that manage energy become saturated or inefficient. Your body protects the pattern by limiting flow when the cost becomes too high. Rest is not the absence of motion. It is a shift in how motion is organized. Energy continues to flow, but along different pathways. Repair replaces exertion. Heat dissipates. Balance is restored temporarily. Even thought itself fits into this framework. Thinking is not an immaterial process layered on top of physics. It is a pattern of electrical and chemical motion in the brain. Neurons fire. Neurotransmitters are released and reabsorbed. Energy is consumed and redistributed. The continuity of consciousness depends on this motion remaining organized. Interrupted abruptly, and awareness ceases. Restore it, and awareness returns, not because something non-physical has been reinserted, but because the pattern has resumed. This makes the connection between motion and identity unavoidable. You are not something that has energy. You are something that energy is doing for a while. This does not mean that individuality is an illusion. It means individuality is dynamic rather than static. Your boundaries are real, but they are maintained, not given. They exist because energy flow keeps them intact. Skin, membranes, immune systems, and regulatory processes all serve one purpose: to maintain a distinct pattern of motion against the background of the environment. They do not isolate you completely. They manage exchange. Without exchange, the pattern collapses. Too much exchange, and it dissolves. Life exists in a narrow band between isolation and dissolution, where motion can be controlled without being stopped. This balancing act mirrors the larger story of motion in the universe. Structures persist when energy flow is regulated. They disappear when regulation fails. Motion never ends, but patterns do. Seeing yourself this way also reframes aging. Aging is not energy running out. It is the gradual loss of precision in how energy is managed. Repair processes become less effective. Errors accumulate. Coordination weakens. The energy flowing through the system remains. What changes is the system's ability to direct it into maintaining structure. Eventually the pattern becomes unstable. The flow continues, but it no longer sustains the same organization. The pattern dissolves back into the larger motion of the environment. This is not unique to living beings. Stars age in the same way. They do not run out of energy in the abstract. They exhaust specific pathways for organizing it. When those pathways close, structure changes, motion continues. The temporary nature of patterns is not a flaw in the universe. It is a consequence of how energy moves and how probability shapes organization over time. Stable patterns exist where conditions allow them. They persist as long as those conditions remain favorable. This perspective also changes how beginnings and endings are understood. Beginnings are not creation events in an absolute sense. They are reorganizations. Endings are not annihilations, they are dispersals. Everything that makes you physically real is borrowed from the universe and will be returned to it, but nothing is lost. Motion continues through different arrangements. This continuity is not something you need to imagine or accept philosophically. It is built into the physics. Energy conservation guarantees it. Entropy explains its direction. Motion persists whether patterns do or not. Understanding yourself as a temporary pattern of energy does not strip life of significance. It places it within a larger, consistent story. It explains why continuity matters more than permanence, why process matters more than possession. It also clarifies why moments matter. The pattern exists now because energy is flowing now. There is no static version of you waiting somewhere unchanged. There is only the current state of the flow. From this viewpoint, stillness is not peace, and motion is not chaos. Both are aspects of how energy is arranged. What matters is coherence. You exist because coherence is being maintained. You will stop existing when it is not. Motion will continue either way. And this realization leads naturally to the final step in the discussion. If motion never ends, if energy is conserved, if patterns form and dissolve, then what does it mean to talk about an ending at all? What kind of conclusion can there be in a universe where nothing truly stops, only changes its form? To answer that, the focus must widen one last time, not to introduce a new idea, but to bring everything together, returning to the original question with a clearer understanding of what motion really is and why it never reaches a final rest. By the time everything is laid out, the original question no longer sounds like a challenge. It sounds like a description. Motion never ends, not because the universe is restless or unfinished, but because there is no rule that allows motion to disappear. What we call endings are rearrangements. What we call stopping is redistribution. What we call stillness is motion that has slipped below the threshold of what we can easily perceive. At the beginning, motion felt like something fragile. It looked like an event with a clear start and a clear finish. Things moved, slowed, and stopped. Effort produced motion. Fatigue ended it. That story worked because it matched daily experience, but it was incomplete. It confused visibility with existence and coordination with presence. Once energy entered the picture, that confusion began to clear. Motion was no longer a thing that had to be sustained. It was one of the many ways energy could be arranged. When motion faded from view, energy did not vanish. It changed form. It spread. It became heat, vibration, radiation, microscopic activity. The movement was still there, just no longer gathered into a single trackable path. At smaller scales, this became unavoidable. Atoms vibrated. Particles moved, fields fluctuated, even the most solid, quiet objects turned out to be full of activity. Absolute stillness became not just rare but unreachable. The closer physics looked, the more motion it found. At larger scales, the same persistence appeared in a different form. Planets orbited, stars moved, galaxies flowed through space. the universe itself expanded. Motion was not the exception, it was the background condition. What changed over time was not whether things moved, but how that movement was organised. Entropy gave that change a direction. Energy spread out because there were more ways for it to be spread than concentrated. Organised motion dissolved into disorganised motion not because anything was being lost, but because probability favoured dispersion. Motion became quieter, less structured, harder to reverse, but it never stopped. Even life fit into this picture without breaking it. Living systems did not escape entropy. They used energy flow to maintain temporary pockets of organisation. Life existed because motion never ended, not because it was exempt from the rules governing motion. When those patterns ended, energy continued on, indifferent to the names we give to its arrangements. By the end, the idea of an ending itself had changed meaning. Endings were no longer absolute. They were local. A machine stopped. A body ceased functioning. A star burned out. But none of these events erased motion. They redirected it. They closed one pathway and opened others. The universe did not move towards silence. It moved toward uniformity. And even uniformity was not stillness, only balance. This reframing strips motion of drama without stripping it of importance. Motion does not persist because it must achieve something. It persists because nothing forbids it from doing so. Energy cannot be destroyed. Motion, as one of its expressions, has no final state where it is required to disappear. What changes is scale, structure, and accessibility. Motion that once powered wheels and muscles becomes heat in air and ground. Motion that once shaped stars becomes radiation drifting through space. Motion that once sustained a living pattern becomes part of the environment that sustains others. Seen this way, the universe is not a story with a climax and an ending. It is a process with transitions. Structures arise, persist for a time, and dissolve. Motion flows through them all, indifferent to their duration. Nothing ever truly stops because stopping is not something the universe knows how to do. It knows how to transform, to redistribute, to balance, to spread. It knows how to let motion fade from one form and reappear in another. And that understanding does not close the conversation so much as it quiets it. The question that began as a puzzle becomes a background assumption. Motion continues whether it is noticed or not, whether it is useful or not, whether it takes forms that matter to us or not. There is no final rest waiting at the end of things, only different ways of moving, arranged differently, over timescales that stretch far beyond any single pattern. And somewhere within that ongoing rearrangement, motion continues to pass through moments like this one, briefly organised enough to be noticed, before drifting onward again without ever needing to stop.